Good evening, everyone, and happy Friday. I hope everyone has enjoyed the first week of class. At the end or conclusion of class later tonight, you'll be officially one quarter, 25% of the way done with the class, which is always exciting. We still have plenty more to cover here. But let's go ahead and jump right into it. I don't have too many announcements for today, but let's just see what we're going to be covering. As you know, we only made it, as I said, on Wednesday, about halfway through the flight instruments. We were, at least got into part of the pitot-static system. So at this point, obviously, our number one task for today is to finish up the flight instruments and then move on to our new material in airspace. So we will pick up with the remainder of the pitot-static instruments. Then we'll move on to the gyro instruments. So that's a total of 4 instruments together that we have to cover. We'll also go into the compass and compass errors, and then we'll switch gears and talk about what you can actually find on an aviation map. So there's 2 different types of maps. There's an aviation sectional map, which basically covers a larger geographic area. It could be composed of, multiple states, or for example, in California, there's basically a NorCal and a SoCal one. And then the second type of chart we'll talk about is a TAC chart, which is a more detailed chart for basically metropolitan areas. So most major cities will have some type of TAC chart. So whether you're flying out of Dallas-Fort Worth area, or Los Angeles, Seattle, DC, Boston, any of these major metropolitan areas, they will basically have a sectional chart and then a TAC chart for the local metropolitan area as well. After we figure out what we can actually find on these charts and basically go over that information, then we'll start talking about the actual airspace. So there's 2 different major classifications of airspace. The first one is controlled, which will cover class Alpha, Bravo, Charlie, Delta, and Echo. And then the second one is uncontrolled, which is everything else, in class Golf. We'll get into special use airspace, restricted, prohibited, MOAs, alert areas, and so forth. And then we'll also talk about what are the requirements to be inside of each one of these different types of airspace. So generally, there's going to be some type of visibility requirement, how far we can see out from our aircraft window. And then there is cloud clearance requirements. So for basically all of the different types of clouds out there, there's basically a distance above, below, and horizontally from that cloud as well, depending on the airspace, and also depending on if it's daytime or nighttime. Just as a quick reminder, though, I do appreciate, I think it was American Pet Transport that pointed this out in one of the lessons for today. There is a FAA PDF that we do include out there, which is basically the chart user's guide. As a quick reminder, the one that we've uploaded, I believe, is the 12th or 13th edition. So there is a newer edition that I'll basically post at the end of class today. But this new edition doesn't include any changes for the VFR for you guys, at least this class. It only has changes on the IFR side of the house. So there will be no difference in that section. But I do appreciate you pointing it out so we can get that updated and corrected for you. So with that, the other thing we're also going to be covering on this coming Monday, December 5th, if I had my date right, I think that's correct. December 5th here is going to be the federal aviation regulations. If you guys want to take a screenshot of this, we'll also post this. This is actually posted in the homework section as well over the weekend. So if you're following along in Rod Machado's Private Pilot Handbook, all you need to do is review Chapter 6, which covers the FARs, or Federal Aviation Regulations for short. If you're not following along, or if you have a different textbook, a lot of other textbooks like Jepson and ASA, Gleim, etc., they don't necessarily have a FAA FAR section. So you can always look these up on your own, but the only reason I'm providing them to you is these are some of the regulations that we're going to be covering. Now, we will cover everything that you need to know in class, but if you want to kind of jump ahead and see how they're written and where to find them, there is an entire book on this called the FAR AIM, and it's usually produced by ASA, which is a book company out there. There's a number of other manufacturers. I think the ASA 2023 version should be out at the moment, at least on Amazon when I last checked. But you can always Google these online by just putting in FAA, and then you could put in Part 1 or Part 61. You can basically see some of the areas that we're going to be covering. So the 3 sections for Monday is we're going to talk about some definitions that you need to know. We'll get into pilot licensing. So this is everything from how you get your FAA medical, how do you actually, what can you do and what can you not do as a student pilot? And then there's some other new regulations, what can you do and what can you not do once you become a private pilot or a licensed pilot. And then we'll spend the majority of our time on part 91, which is a very large section. So I don't expect you to memorize it, but if you want to thumb through it prior to Monday, these will be kind of the areas that we'll be covering. Once again, if you have Rod's book, it makes it a lot easier because he throws all the necessary regulations in his textbook. Some of the other textbooks don't, or if you don't have a textbook, not to worry. You can basically just Google these or take a look in a local FAR AIM. Okay. So thank you. American Pet Transport said the 2023 is out. That's awesome. So it looks like they're out and available. Thank you for that. So with that, let's go into my little public service announcement here. As I always said, I'll try to keep these short and sweet because we have a lot of information to cover. And then, as I said before, whatever I am unable to cover for the purposes of effectively, I guess, today, we'll basically pick up on Monday, but I'll do our best to get through as much as we can. So there is no catch to this class. You guys have access to live stream in 3 different locations. We do provide all the handouts, the documents, the quizzes, and the final exam, including the written test endorsement from our team of instructors here at the very end, assuming you meet the criteria. So once again, all you need to do is watch all 12 of the lessons. Does not matter whether it is live and or recorded. You can mix and match on the platform, whether it's our website, YouTube, or Facebook. And really the only thing that we do at the end of the day is we will basically pull the access at the end of class. So once all 12 lessons are watched, at the very, very last day of class, which for us is going to be on Wednesday, December 28th, a little bit unusual, but it's because of the holidays mixed in between. You'll basically, that is when the final exam becomes available. The final exam is a total of 60 questions where we do our best to mimic the 60 FAA-like test questions. And you'll basically be timed on that. It'll be 2.5 hours. Most people will complete it in about an hour, hour and a half for the most part. And you have unlimited attempts at it. So once you take it, if you're still scoring above an 80%, I still say keep continuing taking it because the questions are always going to remix and rejumble. And it's actually going to get you more prepared at the end of the day just because of the fact that you're going to see more, be exposed to more FAA test questions at the end of the day. That's really the whole purpose of this. So at the conclusion of class, so 5 days after our last day, will put us on Monday, January 2nd, and that should actually say 2023, so not 2022, but 2023 at 11:59 p.m. Pacific Coast time. The reason why we shut it down, as I've always said, is it gives us a higher completion rate. We're currently hovering around 95%. We've had over 100,000 people take our classes over the last couple of years. 95% of them have actually taken and passed the entire portion of the class. And then 99% of those folks who go on and take the FAA exam pass it on the first attempt. So kudos to all of them, and we want to include you in the bucket. Everybody who started with us on day one, we want you to finish with us. We do know that life and things kind of get in the way. So as a quick reminder, we do also have our private pilot lifetime membership as well that's available to you. So if you feel like you need any additional time, it's a perfect opportunity to, and you like our teaching style, that is as well. Perfect opportunity to support what we do. As a reminder, Check Ride Prep Foundation is a nonprofit. We are run by volunteers, including everybody from our mods to the host, which is me, myself, and then the technical team on the back end. And we can basically only continue doing this from support from, as we like to say, the PBS version, viewers like you. So we do appreciate it if you can support us. But the private pilot lifetime membership, if you realize that you need additional time beyond January of next year, this will give you the lifetime membership with all the updates for the private pilot ground school. You guys have access to the live classes in the future, and then also the pre-recorded version. So the pre-recorded version we do in a studio environment. There are no breaks, interruptions, anything like that. Instead of watching 12 3.5-hour lessons, it's actually like watching 60 to 70 mini lessons where we can actually include a little bit more information, just because of the fact that we're not under the gun with our time. So every time, I'm always cognizant that I need to try to end around 8 or 8:30 here. Sometimes we can include more information in that regard. Plus, if you're in the class and you want to jump ahead, you can always jump to future lessons if you want to kind of stay ahead of what we're doing in the live class. We always keep it up to date. You'll also have the bonuses that are not available in this class, such as the Private Pilot Flight Maneuvers Guide, which is all the flight maneuvers from A to Z, how to fly them, and what you're going to be expected in the airplane. You'll also have access to our companion guide, which is about 900 pages of PDF guide. Includes 120 pages of course notes that our CFIs in the past have put together, and it's broken out by basically individual lesson. It includes everything that you need, plus all the supplemental information. You also have access to unlimited practice quizzes and exams, which is somewhere around 900 FAA-like test questions for this portion of the private pilot. You'll have access from our team of instructors. You'll also get the FAA written test endorsement and the wings credits. So there's no rush if you need more time, or more likely than not, you're not going to be taking your check ride for a couple months, and you usually want to refresh yourself on all this material prior to your check ride. It's a good idea to have access to it at a later point. You'll also have access to the past webinars and the live seminars and the Q&As. So you can always find this in the store section, or just basically find this on our website, portal.checkrideprep.com. And you can basically search for the private pilot ground school package, and that's there for the taking. So with that basically ends my public service announcement. Let's go ahead and move in for the purpose of today's material. As I said before, we've got a lot of information that we have to cover. Let me just grab a drink of water here. So let's go back to the world of flight instruments. So that was my public service announcement. Try to keep them brief as possible. So let's get back to what we need to cover, since we've got a lot of stuff to do. So when we left off, we talked about the pitot-static system. And if you guys remember, we talked about the airspeed indicator. And there's 3 different instruments that basically work within the pitot-static system. The airspeed indicator was one of them. And you guys, I think the last thing we did at 8:15 on Monday, or Wednesday that is, was we basically covered the material on the airspeed indicator and the color coding with all of the V speeds that they're going to ask you. So we're going to go ahead and look at the other 2 instruments. Sorry, just shaking the vertical speed indicator here. And this is going to be primarily the attitude indicator, the vertical speed indicator, and also your altimeter, which are part of the pitot-static system. So with the altitude, this is the altimeter that we're going to be talking about next. We've got to go through a few different definitions here. We're first going to talk about density altitude. So the density altitude, there's 3 different factors that will affect density altitude. There's the pressure, which is basically how high you are. So if you're starting off at sea level down by, let's say, Los Angeles International versus someone up in Big Bear, which is 6,000 feet higher, that will be an effect. Temperature, the hotter it is, the higher the air density, and then the humidity as well. Okay, so basically the higher the temperature, the higher the humidity, and the higher the pressure. Those are all going to affect density altitude. We're going to talk about these in greater detail. I just want to give you a rough overview of density altitude. It is critical. We will cover how to calculate density altitude once we get to performance in about 2 weeks, so don't really worry too much about it. But the main thing you kind of want to think about is the ability. So as you climb, the ability of the engine to produce power decreases due to the reduced air density. Okay. So when you take off from sea level in a 160 horsepower engine, you're probably going to get a climb rate somewhere of 800 to 1,000 feet per minute. If I do that same takeoff with the exact same aircraft at Big Bear, which is starting at 6,000 feet, and let's assume it's just a nice cold day up there, it just snowed, I'm not going to get 800 to 1,000 feet per minute. It's going to be a little bit worse than that. I might get 500 feet per minute or so forth. Well, still taking off at sea level, my engine is going to think that I'm taking off at 4,000 feet if it's 100 degrees outside. Okay, so it will act as if it's trying to do a climb at 4,000 feet due to the density altitude. All I want you guys to know at this point is just that it will decrease. It's going to basically, your engine is, the power that your engine is going to produce is going to decrease due to reduced air density. We will talk about the mechanics and the safety implications and how to calculate it a couple lessons down the road. Okay. All right. The other thing I also need to mention to you guys is we also have this thing called standard atmosphere and temperature. These are 2 values that I would write down and kind of commit them to memory, and they are based off of sea level. So the numbers that we have are 29.92 inches of mercury. That's the HG. And our standard temperature at sea level is 15 degrees Celsius. 15 degrees Celsius, which would actually translate to 59 degrees Fahrenheit. Now, when we're looking at the altimeter, there's a couple different things I'll point out. Within this little window here, we call that a Colesman window, and that's basically where we put or adjust our altimeter setting with whatever the barometric pressure is.
So standard temperature is 15 degrees Celsius. Standard pressure is 29.92 inches of mercury. And this is all based on sea level. The reality is that it's never ever, it's very, very far and infrequently that it will actually be those standard values. Okay. Sitting here in LA today, near sea level, it's a 90-degree day, which means that it's well above 15 degrees Celsius. Now, the big thing that we want to kind of take into account here is that this barometric pressure setting, anytime that we go up or down 1 inch from any value, 1 inch of mercury is the equivalent of a 1,000-foot change, whether you're going up or down. So in the example I give you, if we basically went from 29.15 inches of mercury to 29.85 inches of mercury, we would just do some simple subtraction there, and we would find that that would be equivalent to a 700-foot increase. Anytime that we're going to take off, we need to have the altimeter setting set to whatever the current local altimeter reading is, or baro reading for short. And don't worry about the mechanics of how to find these. We'll cover that in radio operations, but there's no shortage of actually finding this value or this number. We can get it over the radio, through weather sources and those types of things. Occasionally, you may be flying at an airport in the middle of Timbuktu where you're not going to be able to find it. Okay. And we'll talk about what to do in those circumstances as well. All right. So let's talk about our flavors of altitude. So just like we had different airspeeds, remember we had indicated and calibrated and all sorts of others. Altitude is kind of the same way. So the two main altitudes that we typically talk about are going to be your true altitude, which is also known as your mean sea level, or MSL value. So this is providing your height above sea level, and your AGL, which is your absolute altitude, and this is your height above the ground, or what we say above ground level. So very simply, we can see this airplane flying along here. They're 3,000 feet, and we basically are indicating 3,000 feet on the altimeter setting here, and they're basically 3,000 feet over the sea. Now, as they approach the coastline and basically go over terrain, if we have the mountain at 1,500 feet high, then their absolute altitude is something that will kind of vary depending on the terrain beneath them. So in this case, if we have a mountain that's 1,500 feet high, or terrain that's 1,500 feet high, then they're only 1,500 feet above the ground, even though their MSL value is still 3,000. Okay. So this is something, your AGL value, depending on where you're flying, also really on the West Coast here, where the terrain varies, fairly rapidly from high to low and everything else. Your AGL value is kind of always changing. The next one is your pressure altitude. So this is the altitude whenever you set the Colesman window to 29.92 inches of mercury. So the Colesman window is just this little tiny window in here. So if you're flying along, so you can see here in this example, this pilot has set it to a local altimeter setting of 30.15, so 30.15. If I were to just manually adjust this and put in 29.9 or 2, whatever is indicated on the face of the altimeter would be my pressure altitude. Okay, it would be my pressure altitude. The last one here is your density altitude, and your density altitude is your pressure altitude corrected for non-standard temperature and pressure. So basically, remember, our standard temperature and pressure values are 29.92 inches of mercury and 15 degrees Celsius. So this is a way that we can basically use another chart, which we'll learn in future lesson here, in terms of how to calculate density altitude and kind of go through that equation. All right, so how does the altimeter work? So very, very simple device. You're going to realize that there is really not, or very minute differences between your altimeter, your vertical speed indicator, and your airspeed as well. So very simply, if you were to look on the very back of your airspeed indicator, it's the same type of casing that basically holds this type of device. And it is basically only being fed with information from the static line. So it's basically measuring the static air pressure outside the aircraft. Inside of the casing, you're going to have your aneroid wafer, or basically this little bellows. And if we're at sea level, because there's more atmospheric pressure, that pressure is actually pushing down on that aneroid wafer. So it's compressing it. As you start to increase in altitude, the pressure becomes lower. It's lower atmospheric pressure, or what we say the partial pressure starts to decrease. So there's not as much pressure on this aneroid wafer, and what ends up happening is it slowly starts to expand. Now, keep in mind, this is not expanding inches or anything along those lines. This is typically expanding in millimeters or fractions of millimeters when it does so. And as it basically expands and contracts, it's once again connected with a series of gears and linkages, and that's what we see on the face of your altimeter. There is a way to basically allow us to adjust the altimeter. There's always going to be an adjustment knob on the front somewhere, and it's very simple. All you're going to do is basically just move it clockwise or counterclockwise, and that is how you're going to set your whatever the local altimeter setting, or sometimes what we call the baro or barometric pressure for the local environment inside of that Colesman window. All right, continuing on. Here's that Colesman window in a little bit more detail. So once again, this is the Colesman window. You would basically enter whatever the barometric pressure is, and here's that little knob that you can basically move clockwise or counterclockwise. And all you're doing is you're basically just trying to set, if I told you that the local altimeter setting was 29.80, well, that's over here. So I just need to get that next to this white chevron right there, kind of in the center of that Colesman window. So I'll spin it in whatever direction will actually achieve that. So that way it's basically lined up with that little arrow on the right-hand side. Okay. Pretty simple when it operates. All right, so with the altimeter, there are several different altimeter errors. The first one we're going to talk about is pressure errors, and this is a common thing. This is the reason why we always get a current and updated altimeter setting. Once again, legally, we need to have an updated altimeter setting no more than every 100 nautical miles. Don't worry, it's never we never have an issue with trying to obtain that information. It's readily available all the time. We'll go into how to do that later. So if we are flying from San Francisco to Santa Barbara and we look at the pressure difference, basically we have a high pressure situation at 30.25 inches of mercury in San Francisco, and we have a lower pressure. Basically, the higher the values are going to be high pressure, lower the values are low pressure. And we've got 29.25 where we're basically taking an airplane from high pressure to low pressure. Well, if the pilot takes off from San Francisco and they basically do that 2-3 hour flight down south, and they're going to do the entire flight at 3,000 feet MSL, and they did a great job when they took off. They have 30.25, which is the local altimeter setting, leaving San Francisco, and then they completely forgot about it for the rest of the 3 hours. Okay. As they fly to Santa Barbara, you'll notice that they are still indicating 3,000 feet because they haven't actually adjusted their local altimeter setting, okay, within that Colesman window. The problem with that is that from what we like to say is that from high to low, watch out below. So if you're going from a high pressure to a low pressure, watch out below, because what you're going to do is now the pilot's actually going to be at 2,000 feet MSL, and they're still thinking that they're at 3,000 because that is what they're indicating, because they have not adjusted to the local altimeter setting. Okay. You'll notice that 30.25 to 29.25 is exactly 1 inch of mercury, and 1 inch is the equivalent of 1,000-foot change. That's the reason why the pilot was at 3,000 and now they're at 2,000. So with this, that could obviously lead to some situations where if you don't have a correct altimeter setting, you could be in these types of situations, right? Where you might be having a CFIT incident, which is controlled flight into terrain. So high to low, watch out below. High to low, watch out below. Now, the opposite also is true. If you're going to basically take that same type of situation here, but we're going to reverse it. Now the pilot is going to take off from Santa Barbara. We've got 29.25 inches of mercury, and that is your low pressure. And we are going to go to San Francisco, which is our high pressure, at 30.25 inches. And when the pilot takes off, they're planning on doing the entire flight at 3,000 feet here. And they have in the Colesman window everything set up correctly because Santa Barbara is 29.25. So this is 29.25. They are indicating 3,000 feet, and that's actually correct. But if they don't make any adjustments, they keep that 29.25 for those 3 hours and they fly from a low pressure to a high pressure, what will end up happening is, in this example, same thing. Instead of 1,000 feet lower, they're going to be 1,000 feet higher. They are still indicating 3,000 feet, but unfortunately, the airplane is 1,000 feet higher than what the pilot actually realizes. Okay. So from high to low, watch out below. From low to high, you're higher than the sky, you'll see blue sky. I've heard a bunch of these anytime that we're looking at them. Okay. These are some of the different pressure effects when we're looking at it. Next one that we're also going to talk about with the altimeter is going to be the temperature problem as well. So very simply, what we're going to look at is you're going to notice that all three of these have an indicated altitude of 4,000 feet. So the thing is that we'll start with the one here in the center. So this is going to be a standard day or standard condition. So what we've got is we've got a normal air temperature of 59 degrees Fahrenheit, which is the equivalent of 15 degrees Celsius. Now, if everything is considered standard, what you'll have is your true altitude of 4,000 feet will actually be the same as the 4,000 feet as indicated on your altimeter setting. Now, anytime that we are actually in warmer weather, anytime that the temperature is going to be a bit warmer, then the air will actually start to expand. Okay. So in this example on the left, we have warm air at 100 degrees, and that's going to expand slightly. And the pilot is actually indicating an altitude of 4,000 feet, but they are about 250 feet higher than what they're indicating. Okay, they're 250 feet higher than what they're indicated. The one on the right-hand side, anytime it is cooler, the air will actually start to shrink a bit as well. And once you guys get into your instrument training, you'll realize that we have special procedures if it gets cold enough for the instrument pilots, where they actually have to do something called a temp comp, where if it gets cold enough, they actually have to, make certain adjustments for their altimeters. Now, in this example, pilot still thinks they're at 4,000 feet, but they're actually 250 feet lower than what they are indicating, right? They're actually 3,750. And remember, the true altitude is the MSL. So you can see here in the warmer air, you're usually going to be higher than indicated. And in the cooler air, you're going to be lower than indicated. Now, I'm going to share with you a trick question on the FAA exam. I want to say 60% of you will, 60% of you will probably get this wrong. And just realize that you can ask this question in two different ways. Okay. So here's the question. Kind of think about it. Don't just assume hot versus cold here, but let me go ahead and open it up. How do variations in temperature affect the altimeter? Is it A, pressure levels are raised on warm days and the indicated altitude is lower than true altitude? B, higher temperatures expand pressure levels and the indicated altitude is higher than the true altitude? Or C, lower temperatures lower the pressure levels and the indicated altitude is lower than the true altitude? Think about it before you answer. The first couple answers coming in. Hello, Egan, Minnesota. It's actually where I did my flight training out there at CAE for the airlines. You guys have some very, very hot summers and some very, very cold winters up there. All right, you got about a third of the class in. Take your time, though. Mr. Travis, can you enlighten JB about where the note section is, please? 91 degrees today. Woo, Tricky question, I know. And what you'll realize, guys, is when we go over this, you'll realize your mistake if you may have made one. Right now, we are about 50-50 with the class. So you guys are statistically on track with everyone else. All right, got about 90%, just waiting for a few stragglers here. When your tower tells you to set your altimeter to 3017, then you basically put 3017 in the Colesman window. You're absolutely correct, Jerome. All right, apologize if I cut off anyone, but as you guys can see, we got 41% with A, 41% with B, and the balance of the class with C. So it is kind of a 50-50 here. When we're looking at it, the number one thing that I can tell you, and the reason why people get this incorrect, are the following. So let's first look at the right answer. So the correct answer when we're looking at this is, how do variations in temperature affect the altimeter? If we look at A, the pressure levels are raised on warm days and the indicated altitude is lower than the true altitude. And really, don't even worry about the pressure levels. The main thing that we're kind of trying to figure out here is this final statement. So if you can kind of like sometimes dumb down these questions by cutting out, things that might confuse you. Big component here is this right here. So it's basically saying that on warm days, the indicated altitude is lower than the true altitude. And that's actually the correct answer. Okay, so we had about, like I said, exactly 41% of the class with that. Now, if you look at B here, what we've got is another kind of half-ish of the class, another 41%. So this is higher temperatures expand the pressure levels and the indicated altitude is higher than the true altitude. So it's basically the opposite of A, okay? And number one, this is usually the first one that people mistake, and I'll show you exactly the reason why. So once again, let's go back to the correct answer. On warm days, the indicated altitude is lower than the true altitude. So let's look at the slide that we just saw. My indicated altitude in my example is 4,000 feet. On a warm day, my actual, or what we would call our true altitude, is 4,250 feet. So going back to that test question, the indicated altitude of 4,000 is less than the true altitude of 4,250. That's the reason why they can trick you with this type of question. It's like I said, it's not, once you guys see this, you hopefully won't make that mistake in the future. Also realize that there's the same exact question out there, but a little bit of a different variation. And I could say that the indicated altitude is, instead of being lower than true altitude, I could say that one of the potential answers is your true altitude is going to be higher than your indicated altitude, which would also be true, okay? So just kind of realize that. If we look at B here with the higher temperatures in that same thing, this one is saying the indicated altitude is higher than the true altitude, okay? And that's not true because the indicated is 4,000 and we have our true altitude of 4,250, and indicated is not higher than true, so B is going to be incorrect. And then C, the lower temperatures lower the pressure levels, and the indicated altitude is lower than true altitude. So once again, what we're looking at is basically cold weather, where we have indicated altitude is lower than true altitude. So our indicated altitude is 4,000, and our true altitude is 3,750 in this example. The indicated is higher than the true altitude, or inversely, I could say the true altitude is lower than the indicated. Okay, so you can kind of see how they can flip-flop or kind of confuse you on these circumstances, all right? Once again, A is the correct answer. So great job for those that got it. Hopefully when you guys kind of see that in the near future here, you can kind of pick up on that. Also, with the test questions, just like on SATs or ACTs or anything else, try to cut out some of the unnecessary words that it's talking about. The pressure levels are kind of irrelevant. The question is it hotter or is it colder? And then the indicated versus true. All right, continuing on. I said in rare occasions you might be at an airport or a certain location where you're unable or you basically cannot get a local altimeter setting. And that happens every now and then. You might be, in the middle of the desert or one of these very, very small, like private airports out there. very simply, what you do is you set your Colesman window to the airport elevation, or what we call the field elevation. Pretty much no matter where you are, if you are at any type of public, private airport, military airport, you can, there is a document called an airport facility directory that we'll talk about next week. That will give you the field elevation, and all you're going to do is you're going to basically spin that little correction dial right or left and put in, basically match the field elevation to your altimeter. Whatever ends up occurring or showing up in the Colesman window there, that is going to be your local altimeter setting until you can get it updated with potentially air traffic control or, a weather resource or some other resource out there. Okay. All right. So another FAA test question for you. Hopefully this one will be a little bit easier. Prior to takeoff, the altimeter should be set to which altitude or altimeter setting? Is it A, the current local altimeter setting if available, or the departure airport elevation? B, the corrected density altitude, of the departure airport, or C, the corrected pressure altitude for the departure airport? It making sense to everybody? I get about 50% in. The altimeter, there is a term for an altimeter. It's called a sensitive altimeter, and it's only a requirement for instrument pilots. Basically, a sensitive altimeter is plus or minus 75 feet of field elevation if you have a current altimeter setting in there, for those that were asking that. We get about 90% in. Once again, I think Todd was asking what are corrected altitudes. Try to make the question a bit easier for yourself. And basically you could just cross that out if it's confusing you. So B would be the density altitude, or C would be the pressure altitude. Try to make it as easy as possible if you can. All right, let's go ahead and take a look at this. I apologize if I cut anyone off. I see just a few people still answering here, but we need to move on. All right, so we got about 86% of the class with A, 5% with B, and 8% with C. The A's have it. It is correct. Unfortunately, I think I fat fingered the star in there, so you can basically ignore that. The correct answer is the current local altimeter setting if it's available. And if you don't have it, then we basically use the departure airport elevation. We look it up, we figure out whatever that value is. If it's 1,000 feet, then we basically make sure the altimeter says 1,000 feet. And then whatever is in that Colesman window is whatever the local altimeter setting is while we're taking off. Okay. All right, next thing is how to read these crazy devices. They all come in different shapes and sizes, and these are actually FAA test questions here. Number one, just really pay attention to that 10,000 foot hand. Basically, the 10,000 foot hand will appear in one of two ways. It's going to be usually the very, very shortest hand out of all of them, as we can kind of see here. In some circumstances, they do actually have a line drawn all the way out to the altimeter, which is actually kind of helpful. From there, you have your 1,000 foot hand, which is the big chunky one. And then finally, we have our 100 foot hand, which is the longest hand as we look at it. Always make sure that depending, really pay attention on these FAA tests where that 10,000 foot hand is. And I'll show you why here in a minute. But looking at a few different examples from an altimeter reading here, the first one that we have is at 3,000 feet, and we've got the 10,000 foot hand. If you kind of draw the line up, you can see it's definitely less than the 1. If this was actually pointed at 1, then that means that you're already at 10,000 feet or very close to 10,000 feet. So in this example, we've got the big or the fat hand on 3 and the tall one on 0, which is giving us 3,000. If we look at the exact same thing, the 10,000 foot hand is not even anywhere close to the 1. We've got the fat hand, which is our thousandths, right between the 3 and the 4. So we know we're above 3,000, but less than 4,000. And this is right on 500 feet because that's our hundredths. So that's 3,500. Looking at C, we've got 6,800. You're going to notice that our 10,000 foot hand is getting a little closer to that 1, but definitely below 10,000. The fat hand here, very close to 7. So it's not quite at 7,000 feet. So we know that, and we've got this at 8, so it's going to be 6,800. The last one, if we were to kind of extend that 10,000 foot hand here, and that's not probably perfect extension, but you'll see it's definitely past the 1, okay? Because that 1 is representing 10,000 and the 2 is representing 20,000 when we're looking at that hand. So we know we at least have 10,000, and then our fat hand is on 3, and the tall one, the hundredths, is on 0, and that's how we come up with 13,000 feet. This is another representation of your altimeter. Couple things to point out. You have your barometric pressure over here in inches mercury. That is your Colesman window. Some of the fancier ones also have millibars as well. So if you are traveling internationally and you need that millibar conversion, that is located in there. And then this little black and white barber pole at the bottom would basically indicate that you don't want to trust this device should there be an issue with the static source going into it. All right, so now it's your turn. I do not have a test question for you, but this is pulled directly from the FAA testing supplement. We're going to start with number 1. Go ahead and put in the chat, number 1, what you think the altimeter reading is. Nope, the 10,000 foot hand is actually precise. It is your vision that's imprecise. Most people eyeball it and then they realize their error. So what is number 1? All right, we got 1,500, 10.5, 15, 10.5, basically one of the two here. Break out my ruler. One said 500 feet. All right, so the answers that I'm seeing are basically 500, 1,500, or 10,500. So I always recommend with the first one starting off with a 10,000 foot hand. It's still that little baby thin hand that you see there. And this is a question that you will get on the FAA exam. So when we take a look at this, I'm going to use a straight edge and cheat just a little bit to the best of my digital capabilities here. And we can see that that 10,000 foot hand is pretty much on the 1. Okay, so I definitely have 10,000 feet. And it's probably right on the 1 if I drew that a little bit straighter. The 1,000 foot hand, which is the big chunky one here, we can see that it is above the 0, but it's also below the 1. And I would have to look at my my hundredths, and my hundredths is right on 5. So what I've got is going to be 10,500 feet. Okay. And that would obviously be MSL. Now, the reason why it's not 1,000, I think someone said 1,500 or 500 feet is if that was 500 feet, that hand, that 10,000 foot hand would be much, much closer, if not near 0. So that's the reason why. All right, let's go ahead and try number 2. Go ahead and put in what you think the correct altimeter is reading on number 2, please. Matt's got all of them here. $14.5, $14.5, $14.501. Okay. All right, I think you guys got that one. So obviously, I'll do the exact same thing. I'm going to draw from that 10,000 foot hand. So right here, remember that's my thousandths or 10,000 foot. I'm obviously well above the 1, but I'm definitely below 20,000. So I'm somewhere between 10 and 20,000. So the next thing I'm going to look at is I'm going to look at my hundredths and my thousandths. So let's look at the thousandths, which is the chunky one. So I know I am above 4,000. And the hundredths is the 5. So what I've got is going to be 14,500 feet MSL. All right, and number 3, the final one. Saw a couple people already throw it in there. What do you guys think it is? All right, looking good, everybody. So basically, the class is split somewhere between 9,500 and 19,500. Okay, let's see if we can figure this one out. All right, so you guys either said 9.5 or you said 19.5, so it's got to be one of the two. So very simply, I'll start with that 10,000 foot hand, and if I just draw a line straight up, what you're going to realize is that's my 10,000 foot mark right there. It's either touching the one or just shy of the one. And the reason why 19.5 is actually not going to work is that if it was 19.5, that hand would be closer to the 2 over here at 20,000 feet. It would be basically just shy of that 2. And we can clearly see that that 10,000 foot hand is actually very, very close to the 10,000 foot mark. So looking at my thousandths is right here. So I know I'm above 9,000, but I'm below the 0. And then finally, straight down, that's the 500 mark. So this is 9,500 feet MSL. Okay, good job, everyone. All right, let's do one more before we go on a break here. And this is going to basically wrap up the pitot-static system. And then when we come back, we'll talk about some of the pitot-static errors. So the last instrument that we have of the pitot-static system is going to be your vertical speed indicator. Now, your vertical speed indicator is pretty much exactly designed as the rest of the instruments. Like I said, there's small variations in each one of these instruments, but if you can understand the differences, then it makes it really easy to know what happens in the event that there's a failure within either the pitot or the static side. So very simply, the information is fed through the static source. It has the expandable metal wafer or the aneroid wafer, whatever you want to call it here. It basically expands and it contracts. It's basically connected to a series of mechanical gears and linkages that basically will give the pilot some information on the face. The only difference between this and the airspeed indicator is this little device here, which is called a calibrated leak. It's a small opening that restricts or causes a lag in the flow of the static air pressure within the instrument casing. And basically it allows the device to go back to 0. The VSI provides information, basically 2 pieces of information. It will provide the rate, so the rate and the trend. The trend is basically what initially happens. In this case, if it heads this way, we are climbing. If it goes that way, we are descending, okay? So that would be the trend. The rate information is going to be wherever this needle pauses, that is the rate that you're climbing at or descending at. So very simply, what we've got is this is 100 and that is 0. And what you have is this is the upside. So you're basically going to be climbing at roughly 50 feet per minute in this example. Okay. So you can use this for a variety of different things for flight planning. You can use it to maintain a certain descent or climb rate. Basically, we've got 500,000, 1,500 for the climb, and we got 500,000 and 1,500 for the descent. Most of the time that we climb or descend, we're somewhere between 500 to 1,000 feet per minute, which is actually fairly stabilized when we do so. Okay. Now, the last thing here with the static system is if the static source became blocked for whatever reason, maybe there's a bug that crawled into it or something, or maybe it froze over, there is going to be usually an alternate static. You have to check with your aircraft manual. Majority of the alternate static is going to pull the static air from somewhere inside of the cockpit. A lot of times, if you kind of go in the pipers, if you kind of go underneath the panel on the pilot side, somewhere where the knee, the left or right knee is, you're going to find a little valve underneath. And if you basically twist that valve, it will basically grab, instead of the static port outside, it'll grab the alternate static information from inside. So should your static port freeze over or something happens, you can at least continue flying, even though there's going to be a little bit of a discrepancy in some of the flight instruments, and we will talk about that when we come back from break. So with that, let's go ahead and take that 10-minute break. Go ahead and stretch your legs, recaffeinate, rebourbonate, reburnate, whatever you need, and we will continue with the flight instruments and then move on to aviation charts when we come back. So take care, everyone. See everybody in 10. The last one that I saw, last question, is someone was asking if there's still room on the one-on-ones, and the answer is yes when I talked with Travis just a minute ago. So if you guys are still interested in securing the lifetime before it goes up on Tuesday, that would be the time to do it and get the one-on-one. All right. So we talked about the alternate static system. Just make sure that you understand where the alternate static source is. Keep in mind, this is generic information. 90% or so of the aircraft will have an alternate static source somewhere inside the cockpit. I have seen some of the newer Cessnas with alternates that are actually outside, and it's just a different source. All right, so let's see what happens if something were to block. Now, this document is found in the last lesson because this is a carryover from what we should have covered the other day. The main thing is I would print this out. You will be asked this on your check ride. We're just going to stick with the left-hand side of the chart first. And this is the reason why that it is important to kind of understand how each one of these instruments varies ever so slightly. The very, very first thing, if we had a blockage in the ram air inlet there, but our drain hole remained open and our static port remained open, our airspeed would actually go to 0. And this is the reason why. This drain hole is going to act like the calibrated leak in the VSI, the vertical speed indicator, and that's the reason why it goes to 0. Now, if I were to get a clog on both the drain hole and the ram air inlet, and my static port remains perfectly fine, what will end up happening is that it will act like an altimeter. So if I were to climb in altitude, I would actually get a higher airspeed, and if I were to descend, I'm going to get a lower airspeed. And if this was the case, if you continued the descent pretty much before you even landed, your airspeed will pretty much be at 0 at that point. Okay, and that's what we mean by unreliable airspeed. Now, if that was not the issue, so let's assume that everything was back to normal, but the static port became clogged, what will end up happening is that right here, it will be, your airspeed will be low in a climb and high in a descent. And when I mean low in a climb and high in descent, slightly higher and slightly lower. It's not significant. Now, in the event you use your alternate cockpit static air, meaning that you're pulling the static air from inside of the cockpit and not outside the airplane, your airspeed indicator is also going to read slightly higher, a couple knots higher or faster. And then finally, number 5 is your broken VSI glass. So the VSI is the vertical speed indicator. This would be done as basically the last resort. Probably you'd never have to do this as a private pilot because you guys should always be able to look out the window and figure out if you're climbing or descending, or basically look outside and kind of figure out what is the rough attitude of the airplane. But the VSI out of the 6-pack is one of the least useful instruments. Traditionally, we teach this in instrument training. So if you're stuck in a cloud and, you know, if it came to it and your alternate static wasn't working or anything else, you could actually crack the face of the vertical speed indicator. Keep in mind, it's glass, so you're probably going to need a tough flashlight or something. And then, you know, it will draw the static air in through the VSI. Now, that'll obviously make the VSI completely useless to you, but it's better to at least have your airspeed indicator and also your altimeter working than not. For VFR flights, for what most of you guys are doing, try to think that over. These VSIs, the flight school will probably charge you $500 to $1,000 for the replacement for that thing, unless it is truly an emergency. All right, so looking at the opposite here, so instead of the airspeed indicator, we're going to talk about the other side of the chart. So we've done airspeed. We're going to look at the altimeter and the VSI. So no matter what, even if the pitot tube is blocked, remember that the pitot tube information is only being provided to the airspeed. So there's really nothing that matters there. Both your altimeter and your VSI are going to work perfectly fine because it only gets information from the static source. Now, if that static source was blocked, what will end up happening, your altimeter will freeze. And the reason why it's freezing is that the air pressure inside of that casing has nowhere to go. It can't get higher, it can't get lower, and thus your little wafer is not expanding or contracting, and thus it's basically locked in there. Okay, so it's just going to completely freeze. Your VSI, on the other hand, will basically go to 0, and that's going to be due to that calibrated leak. It will freeze in place, and then naturally it will start to go back to 0. If you were to use an alternate cockpit static source, your altimeter will be ever so slightly higher. And the VSI, you can play with this on the ground. If you were to move that alternate static source on the ground, you'll usually see that your VSI will climb momentarily for like a half a second, and then it goes back down. If you break the face of your VSI instrument, everything will change just ever so slightly. The altimeter is going to read slightly high, and it will still work. And the VSI will actually reverse itself. It goes backwards, so you just have to completely omit that instrument if you ever got into that situation or case. Okay? All right, so that is basically the pitot-static system errors. Remember, for the purposes of your check ride, you will have to draw out the pitot-static system and also explain, just like I did, what happens in the event that the pitot tube becomes clogged, or the drain hole, or both, or the static port also become clogged. So let's look at an FAA test question that revolves around this. There are a couple different variations of this question, so just keep that in mind. Go ahead and open it up. Let me close the last one. If the pitot tube and outside static vents become clogged, which instruments would be affected? So I'm not going to read them all, but there are your potentials. Thanks, Van. I am writing it down right now. What is a 25 November? What is that? What does that, I don't know, specialty, I guess is what it's called, right? About 50% of the class in. I'm looking for, we can get 100% since we've been talking about this for almost an hour now. Tom's, okay. Thanks, Van. Get it, sir. I like your setup that you shared with everybody on your Mac. I didn't even know they had flight sims for Macs, by the way. All right, get about 60% of the class in. Yeah, and keep in mind, guys, when we're saying break the VSI, you know, if you can look out the window on a clear day, there's no reason to break instruments. You should know if you're climbing or descending by basically referencing the horizon in front of you or around the airplane. This is like last minute, you know, maybe you're flying in the desert at night and you have no outside references and you need to get your flight instruments to work, then, you know, that would be your last resort, assuming you didn't have an alternate static source inside the cockpit. Got a lot of military. That's awesome. Thank you again for your service with 11 Bravo. All right. Looks like we got everybody in. Let's go ahead and take a look at it. We got 94% of the class with the correct answer. Just a couple people with the incorrect one, but most of you guys have got it. So we do have the altimeter, the airspeed indicator, the vertical speed indicator. The reason why A and C are incorrect is the turn and slip indicator is actually a gyroscopic instrument. Haven't even talked about those yet. That's coming up here in the discussion. All right. Great job, everybody. All right, so the next thing we're going to talk about is these wonderful gyro instruments. And before we talk about how they actually operate, a lot of the gyroscopic instruments are going to be powered using the vacuum or suction system. Most airplanes will have a vacuum pump. Some of the new ones actually have two vacuum pumps, like the newer 172s actually have two vacuum pumps that operate anytime that the engine is operating. And both of them are always on. Should one fail, then the other one takes over. But every airplane is slightly different. There's also some vacuum systems, let's say on the Piper, that are engine driven. And then they also have a backup vacuum pump, which is effectively for like battery powered. So if your engine quit, you could still, you know, fly or basically use the battery powered one. Now the vacuum system overall, a lot of people kind of draw it backwards. Part of it is you're going to have this thing, a suction gauge, as you guys can see here, inside of your manual, or basically your checklist. When you're doing your run up prior to takeoff, this is one of the things that we're checking. And we basically want to make sure that the suction is within that green section, or some of the older planes, they'll tell you that they want it somewhere between, you know, like 4.8 to 5.2 inches. So you just have to cross-reference that. And that's one thing that we're actually checking. Now, the schematics of a vacuum system, most people think the vacuum pump is on the front end. It's actually on the very, very tail end of the system. Very simply, what ends up happening is there's a vacuum air filter. So this is where all of that outside air comes into. Obviously, we want it filtered before we send it to our instruments. It will send it through the suction gauge in order to basically allow the pilot to verify that there is suction and the correct amount of suction. If there was not enough suction or that vacuum pressure was not enough, then we could basically, we may not be able to rely on the following instruments. So we're going to talk about the heading indicator and also the attitude indicator. That will basically take this vacuum air, this suction, and it's going to spin it. It's going to spin some gyros at high speeds, and very much just like a vacuum cleaner, it's going to suck that air and then basically throw it overboard outside the aircraft. Now, keep in mind, as we cover the attitude indicator and the heading indicator, you just need to make sure that you understand what or how yours are actually equipped. There are heading indicators and attitude indicators that are not vacuum powered. There are some that are electrically powered. There are some like the new ones, like the G5s from Garmin, which are basically digital displays as well. So we're not going to go into all the different nuances, but just make sure that you understand how yours works in your airplane. The attitude indicator is a very simple device, at least for the pilots in terms of what we're looking at. It's kind of like home base, where this is something that we can tell or figure out the general attitude of the airplane, whether it's nose up, nose down, if we're in a turn to the right or to the left, or a combination. So taking a look at it, very simply, the blue is the sky, meaning that we'd be in a climb. The brown is the ground, meaning that we're diving towards the ground. At the very top here, what you're going to have is you're going to have the following tick marks. You will have 10 degrees, 20 degrees. The large one is always going to be 30 degrees, and then it will be 60 degrees. So same thing over here, kind of in the shadows, 10, 20, 30, and then you've got 60. Some of them will have the 45-degree mark here. You'll notice that that is missing, where I put my little question mark on the right-hand side. Sometimes that 45-degree mark will be a triangle. That's just a variation based upon the manufacturer that's making it. The reason why the 45-degree mark is usually shown is that for the purpose of your steep turns, you guys will actually be doing 45-degree banks. You'll have to do one 360-degree turn to the left and then followed by one to the right at 45 degrees, plus or minus 5 degrees during your flight training. When we look at the miniature airplane here, we can see the miniature airplane in yellow, or in this case, it happens to be this kind of whatever that color is, the safety color there. That is basically referencing the wings of the airplane. So when you are on the ground prior to departure and you're doing your run up, you're actually going to make sure that the wings are basically level with the horizon, which is that white line there. And then you have all of these tick marks. So this is 10 degrees nose up, that's 20 degrees nose up, and then sometimes they have 5-degree increments. It just depends on the manufacturer once again. So hopefully, if you're doing everything right and you have it calibrated prior to departure, if we look at the one on the right-hand side, that would basically be straight and level. Maybe a slight turn because we can see here that it is slightly right of that center white mark there. But that could also be that the pilot, maybe they're on the ground and there is maybe just kind of ever so like a little bit of a slope in the taxiway, or they could be in flight and maybe they just have a very, very slight right turn. Prior to departure, during that, you're going to have this device right here, which allows us to calibrate that. Very simply, all it is it's going to move clockwise or counterclockwise. That will actually move your miniature airplane up and down. And all you want to do is make sure that the miniature airplane is basically flush against that white horizontal line there. If you do have a vacuum one, typically somewhere listed on it, it will say the word vacuum when we look at it. Now, the attitude indicators are much, much heavier than the traditional pedostatic system devices. If we were to compare the weights of like the airspeed indicator that I showed you the other day versus the gyro is pretty much pure metal when we look at it. So for the gyro, these are all called gyro instruments or gyroscopic instruments. And very simply, see if I can show you guys this. This is your attitude indicator. So this is one that we tore apart. We can see the black down here, which would be referencing the ground. And then we also have the blue at the top if we were climbing, and then all of the detents and tick marks around it. If we look at the very back of this device, you're going to see a single hole, and that is actually the vacuum source that we have here. And looking inside of this device, this is actually a 3-axis gimbal. So it basically moves on all 3 axes. And the large part where this casing is there is a device in here, and this is what is actually spinning. It's actually a spinning gyro. That vacuum is basically sent through there, and it spins a gyro somewhere between 10 to 15,000 RPM, so revolutions per minute. can of compressed air. If you were to basically put a can of compressed air and try to blow against those nubs, that's actually going to start the rotation of this gyro. And it's a very, very heavy device. Okay. So that's basically grabbing that vacuum air, and then that's what's actually spinning this thing at very, very high speeds. Normally, it can take about 3, 4, 5 minutes to actually get to the speed that it needs to be at. And usually, by the time you taxi and you do your run up and everything, it's going to be more than ready for you to operate and actually use. In the event that you had a vacuum system failure, what you would actually see is you'd actually see a tumble. So you might be flying straight and level, and then you'll realize that you haven't changed anything. You're still flying straight and level. You look outside, and yet your attitude is showing a slight right turn or a slight dip or a slight climb or anything like that, because it loses that stability that we're looking at. Okay. So the way that this sucker works, if anyone here has ever played with a spinning top or anything like that, there's this principle called the gyroscopic principle of rigidity in space. So very similar to the left-hand turning tendencies that we talked about previous to this. So the primary trait of the spinning gyro rotor is actually, like I said, rigidity in space. So going back to Newton's first law, a body in motion tends to move in a constant speed and direction unless acted upon by an external force. So the spinning rotor inside of the gyroscopic instrument maintains a constant attitude in space as long as there's no external forces that act on it to change its motion. The mass and the speed of the rotor, it's the reason why it's so heavy, is going to be spinning typically about 10,000 to 15,000 revolutions per minute. And then the attitude and heading indicators, they both are going to use gyros. And the reason for that is it's an unchanging reference in space. That is, once the rotor is spinning, it actually maintains a constant position with respect to the horizon or the direction. The rotor of a universally mounted gyro is going to remain in the same position even if there is surrounding frames or gimbals or moves. So for all intensive purposes, when this thing gets going and it's stabilized at that 10 to 15,000 RPMs, when we are banking and turning and climbing and descending, the airplane is actually doing that around the stable source. So the gyro is perfectly still upright in the correct position. Okay, it's always going to stay upright. So the next one that we're going to talk about is going to be the heading indicator. And the heading indicator is another gyroscopic instrument. The main difference between the heading indicator in terms of the functionality of the gyro system versus the attitude indicator is the attitude indicator is a 3-axis gimbal. The heading indicator is a 2-axis gimbal. And then the final one that we'll talk about is a turn coordinator, which is actually a 1-axis gimbal. Okay. So the heading indicator is sometimes known as the directional gyro or DG. It can also be known as a horizontal situation indicator if you've got a fancier one, which are usually like $5,000 or more, which combined a few different instruments into one. But the heading indicator, and the reason why we have it is primarily because there's so many errors with our compass. Okay, we don't necessarily want to fly via compass. It's pretty difficult, and we'll talk about that moving forward. So you have your spinning gyro here. And it actually sits vertically. You've got your 2 degrees of motion, so it's a 2-axis gimbal. That is then connected to the face of the card. Same thing applies. Some of these will have a heading indicator on them, so you could actually bug a heading, and you could basically say, okay, I want to fly on north, and you can actually throw that in there. This thing right here is a flag. That's basically telling you that there's not enough vacuum pressure or electrical power, whatever is generating it to basically spin that gyro. So if you did see some type of flag on some of these devices, then you'd basically assume that this information was unreliable. In order to adjust this, you push in, and then very simply you rotate either clockwise or counterclockwise, and what will end up happening is that will actually move the compass face right or left. And before we actually take off, we actually want to make sure that the top here, in this case, it's actually north, whatever this value is at the top matches our compass. And we're actually going to be doing this every 15 to 20 minutes during our flight. These things will do something called precess, or it's basically precession. And what will end up happening is they will start to scoot off of the heading that you set previous to that. So every 20 or 30 minutes, these things could be off about 5 degrees or so. If you've got a really bad one, I've seen them off like 10 or 15 degrees in a 15-minute period. And I've seen really good ones that are only off like a degree or so every 20 minutes. So once again, each airplane, you're going to kind of have to figure out how the instrument is operating. So the way that these operate is still that gyroscopic principle, but the main one that we're going to be covering here is going to be this precession. And precession is just a tilting or turning of the rotor axis as a resultant of the force. So very simply, when a deflective force is applied to a stationary gyro rotor, the rotor will move in the direction of the force. However, when the same force is applied to the rim of a spinning rotor, the force causes the rotor to move as though the force has been applied to a point 90 degrees around the rim in the direction of the rotation. So precession at the end of the day is going to be caused by both friction within the gyro and by the aircraft maneuvering. So this includes the turns, acceleration, deceleration, and precession. The reason why it's so important is it's going to cause a slow drift in the gyro, which results in basically erroneous readings. And that's the reason why we have to cross-check it with our magnetic compass and then make the appropriate corrections as we are flying. So very simply, if this sucker was moving clockwise, we spun this on the table. If I were to put my finger right here on the rim, 90 degrees later in the direction of rotation, basically right here is where that force would be applied. Okay, that's all it is. All right, the final one we're going to talk about as for the six-pack is called your turn coordinator. Your turn coordinator is another gyroscopic instrument, but it's only on a single axis. These are always pretty much, I've never seen them anything but electric. And the reason why this one's electric and not powered by vacuum or something else is it's all about redundancy. Okay, so the reason why you'll know it's electric, a lot of times you're going to see the DC or something similar to that. Some of them will also have the indication of off in there. So it's just like another flag in the event that you lost power to the device, it would show you off, which means that it would be an unreliable source of information. Typically, when you turn on the battery master and you get out to your pre-flight, and you're putting your flaps down and you're checking your lights and those types of things, you're going to hear a whining sound, and it's actually this device that's starting to spin up. It's the first thing that you usually hear when you turn on the battery master. And when you guys conclude your flight and get everything shut down with the engine and then turn off the battery master, you're going to hear this thing spinning down as well. So it does have a gyro inside. There's two different components to this. The first one is the miniature airplane that we see here. And the miniature airplane is going to tell us about our standard rate turn. So very simply, if the wings of the airplane are touching either one, that is going to be your standard rate turn. So that airplane would basically be in this configuration, which means we would be on a left-hand standard rate turn. Now, standard rate turn is the equivalent of 3 degrees per second. And what that would do is that means that we could go it would take us exactly 2 minutes. That's the reason why 2 minutes is always there, to make a 360-degree turn. If I wanted to make a 180-degree turn, I could set my watch and do a standard rate turn. And I could basically roll out of that at 1 minute without looking at any outside references as well. So the other thing that you might also be asked to do, if this is going to be your standard rate turn, if you were to put the wings right here, this is going to be your half standard rate turn. So that basically just slows it down. So instead of 3 degrees per second, half of that is 1.5 degrees per second. The second component of this is the inclometer at the very, very bottom here. So if anyone has ever hung a picture on a wall, a TV, anything like that, you usually pick these up at the hardware store. It's usually a little black ball, and it's suspended in some type of liquid or fluid. Very simply, this is basically going to be known as your slip skid indicator. When I was telling you guys previous to this, like your left-hand turning tendencies, this is primarily what we're talking about. We usually say step on the ball. We want this ball to be pretty much in the dead center here. So if the ball was over here on the right-hand side, because it's on the right-hand side, I would step on the right-hand rudder, and I would apply enough rudder to the point where I could get this ball to basically slide to the center. If the ball was over here, okay, step on the ball. Okay, so in order to maintain coordination, I would step on the left-hand rudder, which means that I would basically start off with very small amount of pressure, and then I would keep adding pressure until that ball is centered. Okay, and this is kind of a constant struggle in order to maintain, coordinated flight. So inside the turn coordinator, this is what it looks like. Very simple device. The inclometer is basically by itself. So unless it's leaking fluid, the inclometer is really never, ever impacted. Here is your single roll axis with the vertical gyro that spins. That is then connected to your miniature airplane, and that is really about it. So like I said, pretty much all of them are going to be electrically powered. The turn coordinator and what you're supposed to feel and look at if you're inside the airplane is we are always looking to fly in coordinated flight. So coordinated flight means keeping that ball perfectly in the center, as I said. In all of these images, we have an airplane that's turning to the right. So we'll look at the one on the far left here. So this will be 1, 2, and 3. So in example number 1, you have two different types of the turn coordinators. This one is newer. The one over here is an older style, but they do the exact same thing. Very simply, we have an aircraft that is in a right-hand turn. They're in a standard rate turn to the right, and we've got a ball that is perfectly centered. So that would be considered a coordinated turn, and what that would feel like as the pilot is your butt should be basically pulled straight down into the middle of the seat if you're doing everything perfectly. In example number 2, we have an aircraft, same thing in that right-hand turn, but what you're going to notice is the ball is ever so slightly to the right. It's in the same side of the turn, and we call that a slipping turn. In a slipping turn, the ball is basically in the same direction as the turn, or what we say inside of the turn, and the pilot is going to feel sideways force to the inside of the turn. You're going to feel like you're being pulled towards whichever way you're turning. In order to correct that, you would step on right rudder because the ball is on the right until the ball centers. And in example number 3, same thing, right-hand turn, except the ball is in the outside of the turn. It's in the opposite direction of the turn, and we call this a skidding turn. Skidding turn is going to be where the pilot is going to feel sideways force towards the turn. Okay, so they're actually going to feel the force kind of towards the outside of the turn, in the opposite direction of the turn. So in order to fix number 3, we would actually step on the left rudder because the ball is the left of center, and we'd apply enough pressure in order to get that ball back to center. All right. That basically takes care of our 6-pack. The last instrument that we're going to look at, which is actually a required instrument on all aircraft manufactured in the United States, is going to be a compass. Okay. So the compass, one of the reasons why we have a directional gyro or a heading indicator, same thing, is because the compass has so many known errors with it. The compass is very simple at the end of the day. It's basically, it's a compass card, and inside the compass card, there is some type of magnetized element connected to it that will point towards magnetic north. And it's then basically surrounded in some type of fluid. So we used to call these whiskey compasses because back in the day, it was actually filled with a beverage-like substance, but that you don't ever want to drink these nowadays. So here is your compass errors. We memorized this using the mnemonic VD MONA. So variation, deviation, magnetic dip, oscillation, northerly turning errors, and acceleration and deceleration errors. So one thing that you guys need to know is that we're going to talk about 2 different types of north. We're going to talk about magnetic north, which is about roughly 1,300-ish miles from the geographic North Pole, or what we would call true north. And then we obviously have true north, which is something that we also use on our charts, and we also have to compensate for that during our flight planning as well. So we'll go through each one of these as we kind of push forward. All right, so first thing is going to be your magnetic variation. So like I said, the differences between your geographic North Pole, which is also called true north, which would basically be if you're standing, maybe on the International Space Station, you look at the very, very tippy top of Earth, or the bottom, that would be the geographic North or South Pole. And the magnetic North Pole is actually a little bit further away from the true tippy top of the world here. Okay, it's about, I think it's like 12 or 1,300 miles away, kind of out by Greenland area. It's not perfectly over the United States as shown. So your magnetic compass is actually going to be pointing towards that. So we actually have to compensate for that. So when we cover the maps and the charts, you're going to notice these things called easterly or westerly variations. Pretty much all over your chart, you're going to have something called an isogonic line. So here we've got 12 degrees, 30 minutes east. And we would either have to add or subtract that when we're doing our flight planning. We'll cover that later. So basically, for most part of the country, you have an easterly variation. For anybody pretty much on the northeast side of the country here, you're going to have a westerly variation that we'd have to compensate for. Basically, east is least, west is best. East is a number. If we see the east, we usually subtract the number. If we have west, we actually add the number, but we'll go through the mechanics of that as we go through flight planning. Deviation is another concern. So there's always going to be a deviation card right beneath the compass. And very simply, all the different components inside of your aircraft radios, the steel and iron components and everything else, they have the ability to basically affect the reliability of your compass. So what the mechanics do is they take it out to basically a compass rose somewhere on the airport where it's basically labeled correctly. And then they basically will figure out whatever the error is, which would be called the deviation. So, for example, we can see here if I wanted to fly north, which is 360, I would actually have to subtract 1. So I'd actually have to fly 359. If I wanted to fly 030, it says +1. So I'd actually have to fly 031 and so forth. So this one's actually a really, really good deviation. I've seen some where they're like 3 or 4 degrees. So that's the reason why it's a lot easier to use a directional gyro. Plus, these compasses actually work a little bit backwards. They're not going to move in the traditional sense. So usually when you're on a right-hand turn, the numbers, people just get it confused. Okay. All right. So that is magnetic deviation. The next one is going to be magnetic dip. Hopefully no one here experiences this, but the compass is actually going to tend to dip towards the magnetic pole. And this is going to be obviously most, the higher or the closer you get to magnetic north, or what we'd say the most dominant or higher latitudes, this will be more of an issue. Now, what ends up happening is that when you're at the magnetic north, then the problem with it is that it starts to actually pull, and that's the reason why we call it magnetic dip. And this will usually happen when you're about 300 miles of the poles. This also applies for obviously the South Pole as well, but pretty much North Pole is what it's compensated for. And if you're within 300 miles of the poles, then the instrument is going to be considered unreliable due to the extreme errors. And then the way that manufacturers work with this is that the south end of the compass is actually weighted to try to minimize this error. Honestly, I don't think any of us are going to be flying that far north where this could occur, but that is a possibility. After magnetic dip, we have something called oscillation. I don't have a slide for it, but oscillation is, just think of it as like jiggling, or basically this compass card here is basically floating in some type of fluid. And usually in turbulence, whether it's light or moderate turbulence or worse, this thing's going to be moving back and forth, right and left, and shaking like a hula dancer to the point where you're not going to be able to get an accurate indication of the direction you're going. You might figure out, okay, well, I'm somewhere between 030 and 240 because this thing keeps swinging between those numbers. But it's something that is you're going to have trouble getting an accurate indication anytime you're in turbulence moving forward. Okay. All right, the next one is going to be your northerly turning errors and acceleration, deceleration errors. So your acceleration, deceleration errors, we have another mnemonic for you. It's called the ANDS mnemonic. Okay, so accelerate north, decelerate south. So very simply, this is most likely going to occur if you're on an easterly or westerly heading. So if I had my airplane here, and I'm going to make up my own airplane. So my airplane is moving in this direction, and this is going to be eastbound, which is 090 on the heading. If you speed up, if you accelerate, what will end up happening is that the airplane, and it's not the airplane still has the same track. It's still tracking 090. But if I punch the gas and accelerate, the compass is going to show a momentary turn to the north. Now, as I basically, as soon as it kind of stabilizes and you didn't make any course changes, you'll realize that you're on the same heading. Now, the same thing will apply if I decelerate. So once again, let's assume I went from 60 knots to 120 knots here. And now I'm basically going to reverse that. So here's north and here's south. Well, very simply, if I decelerate the airplane, then the compass will actually show a momentary turn to the south. And then eventually it'll stabilize and go back to my easterly heading of 090. So accelerate north, decelerate south. It's going to be most obvious if you're heading eastbound or westbound. If you're heading, maybe you're not heading perfectly east or west, and maybe you're heading like 060. You'll notice it, but it won't be to that effect. Okay, you're gonna notice it far more if you're on a 090 or 270 heading. All right, your northerly turning errors are the last one, and you've got another mnemonic. It's going to be the UNOS, and I'll go through the first one, which is undershoot north and overshoot south. So. Very simply, anytime that you're going to be making a turn to a true north, basically a 360 heading or a 180 heading, we have to either undershoot or overshoot depending on what our goals are. So I need to make more room in this PowerPoint, but here is your airplane, and my airplane is basically heading eastbound to 090. My goal is to end up on 360. Okay, my goal is to end up at 360, which is north. So very simply, if I was just using the compass itself, what you want to do is you'd make that left-hand turn. And what I would end up doing is I would probably, based upon experience, I would start to roll out at about 030. And that is the reason why I'm undershooting north. I'm undershooting to getting to that point. Now, the reason why I choose about 30 degrees to undershoot, or it's usually somewhere between 20 to 30 degrees, is that's just based on my experience of the aircraft and the amount that you need to undershoot or overshoot. So once again, you can practice this with the airplane that you're flying. Not all airplanes are going to be 30. Some might be 20. Some might be 15. But the closer you're trying to get to north, that's the more you're going to have to undershoot or overshoot, depending on which direction you're heading. Now, if I start to roll out at 030, because I'm undershooting, eventually you'll realize that I'm actually perfectly heading north. Okay, so I just need to do that for the purposes of the compass because of that lag that we have. Okay, so the next one that we'll talk about is basically the same thing, but we'll talk about the other situation of overshooting south. So same principle, I am flying along and I am on my easterly heading here and I want to turn towards south, which is 180. In this case, I want to overshoot south. Okay, so what I would do is I would basically make my right-hand turn and I would want the compass to point somewhere about 20 or 30 degrees beyond south. So remember, south is a $180, $190, $120, I'm sorry, 90. I'll probably do like 210 degrees. And once my compass says 210 degrees roughly, I will roll my wings level and magically the nose of the airplane and the compass are going to basically scooter back to about 180. So once again, you have to kind of figure that out, whatever that value is. Most of the trainers that I've flown, they're somewhere between 20 to 30 degrees. Now this will still apply even if you're headed south. So I'm just trying to give you the most extreme example. So for example, if I told you to go from a 090 heading to, let's say, 150 degrees over here, you would still overshoot 150, but you may not have to overshoot by 30 degrees. You might have to overshoot by 20 or 15 degrees. You just have to kind of guesstimate that. But these are all of the reasons why it is very difficult to be flying utilizing just a compass due to all of those errors. Okay. All right. So hopefully you guys understand that. And we are finally pushing on to airspace. Okay. So we're going to get to aviation charts and airspace. If you have your chart available, feel free to pull it out. If you do not have a chart available, there are some resources that you guys can use. Anytime that we're basically covering this information, you can basically follow along, or, you know, there's the resource that I would recommend is going to be skyvector.com. It is a free resource. Let me go ahead and pull it up and I'll share my screen with you guys, skyvector.com. So when you go to skyvector.com, this is the one I always like to use in class that you guys can see here. If you end up seeing a white chart that looks very similar to this, this is because this is an instrument chart. You're going to realize at the very top here, it's got all of these different buttons. The one that we're looking for that I would recommend you stay in is the World VFR. The World VFR basically takes all of the charts and it stitches it together for all the FAA charts. As you zoom in, you'll realize that some of these are going to change. So this is just the LA Basin area. Any of the H or the L charts, those are basically high charts or low charts for instrument. You can ignore those. So if you end up clicking on anything that looks white, then just realize you're on an instrument chart. There is a TAC chart that's available. So TAC charts we'll talk about here in a minute. There's also, so here's your LA TAC chart, and you'll see that it just covers the LA Basin. It's mainly a zoomed in version of the LA Basin because there's a Class Bravo airport, a large airport. The other one that we've got is the Los Angeles sectional chart, which basically covers from the Mexico border all the way down to the south to pretty much the middle of the state. And you can even see Las Vegas in the upper right-hand corner. So keep that in mind. If you're looking for the legends or anything else, make sure that you're using one of those. You don't want to use the World VFR because it stitches everything together. As you can see here, I'm not going to get the legends. But if I click on one of the names, like this is the San Francisco one, I can usually zoom out and you can then cross-reference the information on the legend. So every single map has a legend that looks just like this. I would encourage you, as we're kind of going through what you're going to find on the chart, to kind of look at this, and this will be a good starting point to kind of, figure out what you can actually figure out, I guess. And then when you run into an issue or you get stuck, then you can basically cross-reference the legend. Also realize that the legend is available in the FAA testing supplement, so it is fair game, although I would encourage you guys to know what's, majority of these mean. And then there's a more in-depth legend that is included within this lesson. It's called the FAA Chart User's Guide, and it basically has all of this stuff plus all of the more obscure things this thing only has. This thing is fairly limited, but there's a lot more symbols and different symbology, which has different meaning. So you can find that in the FAA Chart User's Guide, which is also beneath this video as well. Okay, so skyvector.com, that's the one you want. Just make sure you got a nice colorful map. If you guys end up seeing something that looks a bunch like white with black or blue lines, or anything with a lot of white space, you guys are using the instrument chart, so just make sure you're looking at something that looks like a topographic chart. Okay. All right, so before we continue or go on that break, a couple things I want to point out. So obviously for those that are a little bit, that don't really understand how maps work or kind of how things are set up, the main thing that we're going to talk about is lat and long. So latitude and longitude, they're two different things that we can kind of figure out an exact position anywhere on Earth for. So the main thing to know is that we have our lines of longitude, which basically start at the prime meridian in Greenwich, England. I think I pronounced that correctly. And basically anything to the right, which would actually be to the east, would be considered an east longitude. Anything to the left, which is west of the prime meridian, would be a west longitude. Okay. You can think of longitude as a long way, basically up and down the tall way. And then we have our latitude, and the latitude actually starts at the equator. So anything above the equator would be a north latitude. Anything below the equator would be a south latitude. And the further that we get away from these, either the equator or the prime meridian, the higher the number of the values are going to be. The way that you can remember the latitude is think of it like a ladder, right? These are lines of latitude. And if I were to climb up or down, you can think of it like a ladder, right? I can basically climb those lines up or down to go either up further to the north or down further to the south. You will have an FAA test question out there that will ask you the exact position of an airport. And you're going to see lines of latitude and longitude along the chart. Keep in mind, sometimes you have to kind of look along the edges or kind of expand the map a little bit more. But if we were to, if we were asked the question to kind of figure out, let's see, I'm going to choose Summer, this little tiny town right here, or Sumner, that is, that little tiny town in the center there. And we're going to figure out what the lat and long is. So when we look at this, each one of these tick marks is basically a minute. And you've got the tick marks for latitude and longitude. So basically 60 minutes is 1 degree. Very simply, if I were to try to figure that out, I could start anywhere I want. I'm going to start with our lines of longitude. Okay. So this line right here is going to be 93 degrees. And then I've got all of my tick marks, and basically each minute, and then it's basically 10 minutes. The larger ones are 10, 20, and then we've got 30 minutes. Okay. That's the 30-minute mark. So this would be 93 degrees, 30 minutes here. And then I've got all my tick marks, and then that's 40 minutes, 50 minutes. And then over here, it goes from 93 to 94 degrees. Okay. That's basically how it works. And all it is just kind of a tedious counting problem. So what I would do is from the point of Sumner, I'm just going to kind of draw a straight line up, and I could have drawn it down too, but there's obviously writing down there as well. So if I take a straight line, it's not very straight. If I try to do a better straight line and go straight up here, then I can kind of figure out where that intersects. So if I look here, I've got 93 degrees. Okay. I've got 10 minutes here. And then I've got 1, 2, 3, 4, and I'm going to call that 5. So that's basically 15 minutes. Okay. That's going to be my longitude. So at this point, Sumner is going to be located at 93 degrees, 15 minutes of your longitude. The next one we got to figure out is going to be our latitude. So for this, I can just draw a line straight across. Right or left does not matter. I'm going to draw it to the left here, right there. And what I have is I've got a line at the very, very top here. that is representing 40 degrees of latitude, and it's basically going horizontal. So it's this line right there is 40 degrees of latitude. If I go down a little bit further, what you've got is, this is not 30 degrees of latitude, but that's actually 30 minutes. Okay, so that value right down there should be 39 degrees, would be further down beneath the map where it's cut off. So what this is telling me right here is this would be 39 degrees, 30 minutes. Okay. So knowing that, I can then count the tick marks going up, or I can count down from 40. Very simply, I think counting up, 1, 2, 3, 4, 5, 6, 7, 8, 9, probably at 9. You can't really have, I'm just going to go with 9 here, which is this guy right here, because here is our 10-minute mark. So what I've got here is it's going to be 39 degrees, and I'm going to add the 9 minutes in addition to the 30. So that means it's 39 minutes of latitude. Okay, and that would be our position. So that's how you guys can figure that out. They're going to ask you about latitude and longitude. Very simply, just try to find the tick marks to the right and left, expand the map when you see it, and then just kind of use logic as you guys work through the problem, right? All right, any questions with that? Guys are hanging in there. Latitude, flatitude, yep. Think of it like a ladder. Okay, if you guys wanted to climb up or down, see my little yellow highlights going up or down? Those are lines of latitude. You can basically hang onto those like a ladder and go up or down. Okay, lines of longitude are the long, tall ones, right? Those are from pole to pole. Think of it as like Curious George swinging from place to place. You have 2 pairs of readers to see the map. All right, so let's do this. Let's go ahead and talk. Let's go not talk about it. Let's go ahead and take a 5-minute break. When we come back, we're going to do all the map stuff, and we'll get into the first part of Airspace here. So stretch your legs, decompress for a minute, take a breath, and we'll see everybody back in 5. right, everybody, welcome back. And in our final hour here, we're going to basically see what is on these sectional charts or these different aviation charts that are available to us. I see a lot of people are saying they're printing them out for their cross countries. That's absolutely acceptable. Just make sure, just really keep in mind, keep it to scale, because obviously we use specific ruler dimensions and those types of things. So obviously if you print it supersized, then that'll kind of screw it up with your flight planning, but as long as you print it to scale, it should be fine. All right, the two primary charts that are available to us as pilots, there's actually three. The one that I'm not including on here is called the WAC, which is a World Aeronautic Chart. Those are still available in kind of parts of, I think, like Yukon. I think Alaska still has it. They used to be available throughout the continental United States, but they're basically no longer available. The WAC chart was a very, very large chart. Didn't give a lot of detail, but it was mainly used for planning purposes. But those are definitely scaled back. The most common chart that you're going to probably find in use today is called the sectional chart. And the sectional chart basically covers everywhere within the continental United States, Alaska, Hawaii. I think they have one for Puerto Rico as well. So anytime that you're looking at a chart, at the very top, you will see what type of chart it is. In this case, it happens to be the sectional for Los Angeles. They're going to have the primary city name in there. It does not mean that it just covers the LA basin. Like I showed you before, the Los Angeles sectional goes all the way down to like the Tijuana, Mexico area and covers basically San Diego all the way up through LA towards Santa Barbara and pretty much up through the middle part of the state. And you can actually see the very, very edge of Las Vegas in there as well. The main thing to know with the sectional charts is the scale. So the sectional chart does cover a larger geographic area. It's 1 to 500,000 versus the TAC chart, which is 1 to 250,000. And then it will usually show you here, we can see the rough area that I've highlighted in yellow there of the Los Angeles sectional in terms of the area that it actually covers. On that picture, surrounding Los Angeles, you obviously have all of the different other sectionals. So if you're doing flight planning or flying through these areas, you can actually find them fairly rapidly. The number one thing that you always want to kind of keep in mind is that these things basically expire every 6 months or so. So you never want to fly with an expired sectional chart, terminal chart, really any type of aviation chart that you're using for navigation. It goes the same thing with a GPS database or really anything else. You want to make sure you have the most up-to-date information at your disposal. The other thing that I'll also point out here is that you're going to be able to see the TAC charts. So they're the TAC charts, the terminal charts, which are like the zoomed in chart. They're not located in every single city out there. They're pretty much surrounding the largest and busiest airports. If we were to look on this chart right here, basically any area, they use this codification here. So we've got one in Seattle, San Francisco, Vegas, Phoenix, Miami, Orlando, all the DC and New York areas, obviously for Houston and Dallas and so forth. So all those that I circled, anytime that you're operating within an area that has a TAC or terminal chart available to you, they would like you to use that because it's a more zoomed in version of it. Okay. So that's the sectional chart. The next one is the TAC chart. We just call it a TAC chart or terminal chart for short. It will have the name on it as well, and it will say the word TAC. This is 1 to 250,000. It has, in this case, the blue color coding showing that it's the LA area. And here we can see all of those other purple boxes surrounding the areas that do have the TAC. Same thing applies. They're roughly valid for about 6 months. They are set up with the same symbology in terms of the terminal charts, the sectional charts, and the World Aeronautic charts. They're all going to be using the same thing, except for, specifically in these very dense areas. It's a lot easier to kind of see exactly where you should be and shouldn't be in the different types of airspace and so forth. Okay. Now, if you happen to be on a sectional chart and you're unsure of a TAC chart because you don't have one, traditionally what you would see is the boundary of the TAC. So for example, this is pulled from a corner of a sectional chart, and this white bar here that I'm highlighting that kind of goes to the left, that would be your indication that within that area, within that white box, then there is a TAC chart or a terminal chart that exists, and then they'd want you to reference whatever that chart is for those purposes. Okay. Sky Vector is current. Yes, Rob? All right, so let's go ahead and take a look at what you're actually going to be finding on a map, and you guys can kind of compare and contrast. So these are the most common things in terms of if you looked out the window and kind of compared them against the actual chart itself. This is the most basic type of navigation. This is called pilotage, basically comparing where you are or looking outside your window and seeing whatever you see outside the window and comparing what you're on the map. That is the form of pilotage, of just kind of navigating with your eyes visually. So valleys and ridges, they're going to be shown there. These are situated or basically set up just like a topographic map. So the shading, I'll show you the shading here in a second, but this is what you're most likely going to find. So valleys are obviously going to be lighter colors. Ridges are obviously going to be higher or darker colors. The actual color codification is always found on your chart. So sea level is basically a greenish color, and then it starts to move to a sand, and then eventually kind of that brownish color at the very, very top until we basically get to Mount Whitney. That's the 14,491 altitude there. So it's a quick representation of the different terrain and things that you're flying in and around. So, if you're flying maybe in this area, you may not want to cut straight across. You might actually want to follow the freeway to get to Dayton Valley, for example. Just because we can clearly see that the colors are a little bit, they're not as intensely red, orangish, brownish colors. And obviously if you follow that corridor, it's going to be a lower, the terrain is going to be a bit lower. Now, the other thing it's going to include is something called a spot elevation. In this case, it's basically the highest point within a ridge line. So you'll see these all over the place. In this case, they're just black dots with the altitude. So in this case, the highest point along this ridge line is 5710. So assuming you have a local altimeter setting, as long as your airplane is flying above 5,710 feet, you should be good enough to clear it. There's another one down here as well at 4,555 as a spot elevation. Inside of your lines of latitude and longitude, you're going to have, I'm always going to butcher this. I used to call it a quadrangle, but I think it's a quadrangle. I'm pronouncing that correctly. But basically inside of each one of these lines of latitude and longitude, it's basically going to make a box, and you're going to find a very special number in there. And that number is called your maximum elevation figure. Okay, it's called an MEF for short. And what it's saying is that the highest obstacle within that area is going to be, in this case, 2,300 feet. The big 2 is representing the thousands. The little 3 is representing the hundreds. And that could actually be man-made or naturally occurring in these cases. So same thing applies here. If I draw out my little box, anywhere inside of this box, the highest obstacle is going to be 6,700 feet, naturally occurring or man-made. Keep in mind, we use this for flight planning purposes. It does not provide a lot of latitude in the sense that it's not giving you like a huge clearance in order to clear whatever those highest obstacles are. And if you are using it for flight planning purposes, you can obviously see that, it's not 6,700 feet everywhere. If you're kind of in this area up here, that's obviously much, much lower terrain than it is kind of to the southwest here. Now, your maximum elevation figure, if we were to back into this number of 6,700 feet, you can look at this information in the panel of your sectional or your terminal chart. It basically will take whatever the highest obstacle is, add 100 feet, so that would get me to 6,600, and let's see, 66. So let me do 50. 66, so let's say 6,501. Okay, so the way that this works is it's going to take the highest obstacle, man-made or naturally occurring, and I'm just making up this number. And what it will do is, in my example, if it's 6,501 feet is the highest, whatever the highest obstacle is within this box, then it will round up to the nearest hundredth, okay, which would get us to 6,600 feet. And then we always add 100 feet to it. And that's how they come up with your maximum elevation figure of 6,700 feet. So basically your maximum elevation figure will provide you a minimum of 101 feet to 199 feet of clearance. So just keep that in mind. We don't want to fly that close to the terrain for good reason. Sorry, I had to think about that for a second. All right, with that, you also have obstructions listed there. You'll be amazed at how many radio towers are sitting around the country that are 2,000 feet tall. and or other things as well. So the first one that we have on the left-hand side, if you see kind of the upside down V here with a dot in it, this is representing some type of obstacle that's less than 1,000 feet tall. You have two different values next to it. The first one is your MSL value. So it's 632 feet MSL. So assuming that you had a current altimeter setting, as long as you were flying higher than 632 feet, you would miss it. And the second one is your AGL value, your above ground level, which is telling you how tall this obstacle is. So if you were at the very, very tippy top of this radio tower right up here and you jumped off, you would get, you would basically fall 302 feet to the ground. Okay. Symbols that are basically representing larger structures or obstacles are going to be just a little bit larger than what we see here. So we can see these two. And with this, the same thing will apply. You're going to have your MSL value here, so 2,115 feet. And then you have how tall it is. Your AGL value is 2,000 feet. So if you jumped off from the top of whatever that obstacle is, you'd fall 2,000 feet to the ground. In the event that it's lit, you would actually see, actually all of them are lit. I don't want to say that. All of the structures should be lit. In some, using some type of device. It doesn't necessarily have to be strobes, but it's typically going to be some type of red light so you can identify it. If they use high intensity strobes, then you're going to see these little lightning bolts kind of coming off of this device here. So this is an obstacle less than 1,000 feet with the high intensity strobe lights. We saw that with the last one here. We can see on this one on the right hand side that it actually has the high intensity lighting. In the event that it is under construction or they're still building it, here we can see two different obstacles next to each other. It's 600 feet MSL and 300 feet tall AGL, and we've got the term UC. That just means that they're working on it. It is under construction at that given moment, okay? All right, roads, not every single city street and avenue and everything else is going to be listed on there, but they will have major freeways and roads basically drawn as shown here. So here we can see a road on the right-hand side, and that road on the left is exactly, this is in the San Diego area by the Julian VOR. So basically that little squiggly line that's kind of that magenta or purplish color is representing the road that you see below it. Other things that you can use for kind of finding your, using as references and kind of finding out where you are going to be railroad tracks. Those are great to use because you can see them usually for, 20, 30, 40 miles or more in a clear day. They kind of look like freeways. If you remember your Thomas guide, in this case, they're just double. In this case, they're not this. This right here is the 101 freeway. What we're actually looking at here is this black line with the little train tracks on it. That is the railroad. Okay. The double purple line, so single purple lines or magenta lines are actually going to be roads. The double ones are going to be major freeway systems. So what you guys actually see here is this right here is the same freeway, the 101 freeway that goes down to San Diego. And then over here is the railroad, which is the one that I've kind of highlighted over in red. Power lines are also great resources, and you're not going to find your, residential power lines. These are going to be your high voltage transmission lines. The companies that build these, they basically clear cut in straight lines for miles. They're pretty obvious when you see them. So what you're going to see is basically a black line going from point to point with a little tiny power, transmission tower thing that's connecting it. And that's your indication that you do have those power lines as a resource or reference. Okay. All right, shorelines, wharfs, and piers. They're also good if you happen to be in a coastal area or live in a coastal community. So out by Carlsbad, which is north of the San Diego area, we can see a few, and they will actually be, they're actually pretty good references depending on where you're actually flying. This inlet here as well is also a good reference. That inlet on the right is actually listed here on the left on the map. So you can clearly see that. And let's see, that's about it for this one here. Bodies of water are also going to be included as well. So whether it is a lake or anything else, large body of water are usually the easiest to see, and they make really good checkpoints. So very simply, the one on the right is supposed to be the same as the one on the left that you can use. Streams and small rivers are also going to be found on these maps. Keep in mind, especially in the California and Southwest, really pretty much in here in the Western area now due to the droughts. You might be expecting to see water, but it might just be a dry stream bed, as you can see, but they are still going to be listed. Basically, all of these little blue squiggle lines up here are going to be your streams or small rivers. And then obviously your larger bodies of water will actually be outlined as shown previous to that. All of the population centers, major areas where people, basically your urban areas, are going to be listed as well. So during the day, this is supposed to be representational. I think this is French Valley over here. And then we can clearly see the French Valley Temecula area right there. The reason why it's yellow is that's basically indicating that it is the rough boundary of where those urban areas are. In addition to that, if you're flying at night, they're very, very easy to see because of light pollution. So that's how you can basically try to figure out where you are. Especially, if you're kind of in more remote areas flying from city to city, you can clearly see two major sources of light pollution. Then you can kind of figure out where you are in relationship to the actual airport. Smaller towns and villages are also listed. So is it Isabel, I believe. Also Julian right here. That is also going to be listed, and we'll also have the town name. They're obviously much, much smaller. As you can see from the image, when you're in the air, it doesn't look like much, and it can definitely blend into the surrounding terrain. At night, you might be able to see a few flickers of light and then try to figure out your position, but you can clearly see in the back here, we've got this road behind it, which is basically representing what we've got with the magenta line kind of cutting through. And then obviously it's a good source of information for our airports. And there's several different types of airports. Typically, when we're looking at airports, you're going to have an airport that will have a control tower or one that does not have a control tower. So if it has a control tower, that means that air traffic control has some type of responsibility to that airspace. It does not mean that it operates 24/7. Really, only the biggest, busiest airports in the country, like Dallas or LA or Miami, they're going to have air traffic control support 24/7. For most of us out there that do have an operating control tower, you can kind of think of it as like office hours. Sometimes they're there from like 8 to 8 or whatever, whatever they dictate for whatever their internal policy is. The main thing is that if you see an airport that's blue, and you're going to see, we're going to talk about these colors a lot. This is called cyan right here, which is a bluish color. If you have an airport that has that cyan bluish color to it, then that means it has an operating control tower. If you have an airport that has this purplish magenta color to it, then that is not going to have any type of control tower. They never built one. There's not one installed, and so forth. Okay. Now the airports, if they don't have them, they could also have other features as well. You can look at the one on the far left-hand side here. It will kind of show a representation of the layout of the runways. So in this case, the one on the left for the Yazoo County Airport, it has a single runway. You'll see these tick marks coming off basically the right, left, and bottom. Those tick marks basically will indicate that there's services available at this airport. And those services are going to be typically some type of fuel, whether it is self-service fuel or if it's a company that provides it. At the very, very tippy top here, this is a beacon. That just is telling you that there is a beacon available at this airport. You can see it on both of these here. Actually, all three of them. There's the beacon symbol. The one in the middle for Chico Airport in the LA area, this actually is indicating that it has a hard surface runway longer than 8,000 feet. So it actually, anything that's more, greater than the 8,000 feet, then it will actually look more realistic on the representation. So something like this over here, March Air Force Base, which does have 8,000 feet or greater, that is what it will look like instead of the circle because it has the greater than 8,000 feet. Okay. And it's blue, or what we would say that cyan color. So it does also have an operating control tower. The surfaces of runways, most runways that you're probably going to be landing at are going to be paved, but there are variations of that. There are basically dirt, gravel runways as well. So keep that in mind. If you just have an airport with a circle, whether it's magenta or cyan, then that's going to tell you it's between 1,500 and 8,000 feet. And those are going to be the hard surface runways, as you see on the right. If you have a circle with nothing in it, like the Salton Sea here, this means that there's a other than hard surface at least 1,500 feet long, or it could be a soft surface. So in this example, that is your airport. So because it's not actually filled in, there's also another one down here. that's going to tell you that it's something that's not paved. So there's a resource that we could actually go into. It's called the Chart Supplement. It's a green book. We'll talk more about that next week. That will actually tell us what type of, is this gravel? Is this paved? What is this? Okay. Other airport symbols that you want to know is military airports are also listed on here. For the most part, you either need prior permission to fly in and out of a military airport unless it's joint use. So like a good example of a joint use airport would be like Albuquerque, New Mexico. But for the most part, you do need prior permission, or you're just going to need, you're probably just not going to be able to fly there. Now, at any point in time, regardless of any airport that you're flying, private, military, or otherwise, in the event you had an engine failure or an emergency, you do have the right to land at any one of those airports. But I'm sure the military airport probably going to be explaining yourself. In the event that I'm going to skip the open dot for right now, but there is a little tiny open dot right there. That's just indicating there's a VOR on the airport, and that's a navigational device. We'll get into those a little bit, probably in about 2 weeks from now. You will see a bunch of restricted or private airports. Anytime you see the circle with the R in it, that is a restricted airport. It's not actually open to the public. And then occasionally you also see the ones that say private. So this is the Desert Center one, and that is the private airport right there. You can obviously fly into a restricted or a private, but you do need permission from whoever owns that property. Sometimes you can get it, sometimes you can't. Maybe it's friends, maybe you own it, maybe you don't. Next to every single airport, you're going to find an airport data information strip. Very simply, it will give you the name of the airport and some basic information. So I'll look at the one on the right for Chico. This is the Chico airport. There's the airport code, Charlie, India, Charlie. We have a control tower here because this is a nice cyan blue color. So there is some type of control tower. We've got the frequency. The star is going to tell me right there that there's some type of operational limitation that exists. Basically, I would have to go look up, when the control tower is open and closed, because they're not open 24 hours a day. And when they're closed, then we use the same frequency because we have something called a common traffic advisory frequency. Don't worry too much about that. We have a whole lesson on communications. We have our weather information, which is the the AWOS 3. Ignore the frequency stuff for right now. That's not the most important thing at the moment. Beneath that, we have our field elevation. So it's 238 feet. The L right here is indicating that the airport has lighting. The 67 is representing the longest runway available, so at least 6,700 feet. And then we have some pattern information at the bottom. Same thing applies on the left. We got Santa Maria Airport here. It does have a control tower. It has a little star, so they don't operate 24 hours a day. They are 261 feet. They do have lighting for night operations. The longest runway is 6,300 feet. And then we've got some traffic patterns as well. As we basically progress, we'll go through exactly what all those numbers and stars and common traffic advisories mean, but let's just figure out what's on the map first. Then finally, we've got our GPS and also our VFR checkpoints, if that was spelled correctly. So here is home base for us, the Camarillo Airport. And if you were to go into the Camarillo Airport, you'll notice that there are all of these different, basically VFR checkpoints. Now you can use these, and if you use these, for example, the Oxnard Financial Plaza, the Saticoy Bridge, CSU Channel Islands, or the Conejo Grade on the 101. If you were to basically verbalize that you're 10 miles from the Conejo Grade or 10 miles north of Saticoy Bridge or 20 miles west of Oxnard Financial Plaza, the air traffic controllers will know exactly what you're talking about. Okay. If you say that you're 10 miles west of some, school right here that is not charted, then they have no clue what you're talking about. Okay. So remember, when we get into communications, you guys will just have to kind of learn this, but you have to provide your position relative to something. Otherwise, they're not going to know exactly who they're talking to or where you're actually located. Underneath each one of these, you'll actually see a VP. So we've got Saticoy Bridge and here and here and here. So all the ones that I just highlighted in green, those are basically VFR, or basically they're all VFR checkpoints verbally, but underneath that in green, that is your GPS. That's basically the GPS code if you want to plug that in. It always starts with a VP, which stands for a visual point, and then it's going to be some type of alphanumeric after that. So if I wanted to plot a course in my GPS to Saticoy Bridge, it would be Victor Papa Sierra Tango Charlie, and I could use that as well. So that's not something we would tell the controller, but if we were using that as a point navigation and we had the capability of a GPS, we could actually plug that point in because it is charted on the map. All right, the last one before we get into our airspace conversation here is going to be your special flight rules. Your special flight rules are certain areas throughout the country where basically there's a little bit different operation or just kind of special or unique operations that basically have to occur in order to kind of get in and out of whatever the airspace is. So very simply, this is found in our case, this is found on our TAC chart in the Los Angeles area. Los Angeles is a very, very busy area, and keep in mind the way that these systems are designed is you can't just fly anywhere you want. We can clearly see here, this is Los Angeles International Airport for LAX. And the biggest thing that they're always trying to do is this is all designed for commercial aviation, right? All the people who pay to fly and travel around the country in the airlines. There is, on a standard day, about 90% of the time, the traffic flow into Los Angeles is flying this direction, and it usually starts 60 or 70 miles away from the airport. It's usually a straight in. So, if you're a little tiny airplane and you're trying to cross this area, they're not going to be too happy with you, nor are they going to allow it. Okay, so what they've devised is they basically have different areas within the Los Angeles basin where you can cross. They're very specific and they have different altitudes and so forth. So very simply, you just have to read the information on the panel. This one, the Coliseum route, is from 8,500 to 9,500. It will tell us exactly how to fly it. There would be instructions in terms of if I'm going north or if I'm going south, and different frequencies that I'd have to tune into and everything else. Okay, so that's really the general idea behind it. LA is kind of an extreme just because of the fact that it has so many different routes and that type of thing. If I were to show you guys on the LA sectional, go back to LA here, all the way down. Here's the LA basin. If I go to your Los Angeles TAC chart, I go to like the outside panels. These are all of the different routes that get us around the LA area, the Coliseum route, the Hollywood Park route. We have the mini route, the coastal route, and basically everything in between. Okay. So get back to that real quick. Los Angeles TAC. So those are basically all available, and very simply, all you do is just read the information at the bottom. Typically, for students and so forth, even people that are coming into the LA basin, it's not uncommon to fly with an instructor first, just because it is a little bit complicated. So that way people can kind of get a hang of it as well. Other types of special areas that you might encounter are going to be out by, let's say, the Grand Canyon area. So I'm going to zoom out just for a sec. And here's the Grand Canyon. These blue boxes that are basically surrounding the Grand Canyon is going to be a special flight rules area. So they actually have special charts. So if you went to the Grand Canyon VFR chart, what you'll realize is they can't just fly into the Grand Canyon. They have different altitudes they want you at. Basically anything in the purple, they want you above 14.5. But you can fly any one of these corridors as shown here. If anybody wants to do this, I would recommend the Dragon corridor, which is this one right here. And then the Zuni corridor over here. I've done all of them, but there's honestly not much to look at over here. Whole purpose of it is for all of the folks that are paying the big bucks and getting the cool tours. They are at much lower altitudes and they have different routing. For everybody else out there that does not have those special endorsements that are provided to those Grand Canyon tour operators, we actually have to be at certain altitudes within each one of these corridors. And typically it's going to be listed somewhere on the edge of the chart, typically somewhere between, I think, 9.5 and something else. So that's another example as well. And then another one would be in the Washington, D.C. area. I'll get to that one a little bit later because that is special. Those are special flight rules as well. All right. So that is the special flight rules in a nutshell. So just pay attention. If there is something particular that they need you to do, just check your chart. And that's really about it for right now. All right, so that is what you're going to find on an actual chart. And those are just probably some of the highlights. Keep in mind, there's a lot more than that, than what we just covered, but there's only so much time. So at the end of the day, the National Airspace System, I would say pre-COVID, pre-pandemic, we normally had about 7,000 flights overhead, and we served about 47 million customers. I'm sorry, it was actually 47 million flights, commercial operations per day, with about 2.2 million customers on an average day. And this whole system is, as I said a minute ago, really designed around the Part 121, the airlines, and those cargo operators that are paying all these taxes and facility fees and everything else. As general aviation pilots, we do benefit from the system. So the number one priority within the National Airspace System is really moving all that other transport and transportation through the IFR system. But all airlines fly instrument; they don't fly a VFR, even if it's a nice, pretty day out. And we'll talk about those differences here now, actually. So you're going to hear these terms. We usually say VFR and IFR. So this whole class is dedicated to visual flight rules, and we're going to go through those rules on Monday. There's another set of rules called instrument flight rules, and that you'll actually learn about that if you end up getting your instrument rating. So very simply, as you can see on the right-hand side, that is a VFR environment, and the whole purpose of the visual flight rules is depending upon the airspace that you're flying in, they will basically dictate how high above a cloud, below a cloud, and horizontally from a cloud you need to be. And then how many statute miles of visibility can you actually look out the window and see? Okay. So you have to maintain the cloud clearance and also the visibility requirements, and every airspace is just ever so slightly different. Okay. You're going to be expected to know those values, and that's what VFR is. We also have something called basic VFR. So basic VFR is the following. It is going to be a 1,000-foot ceiling and 3 statute miles of visibility. Okay. And a ceiling is defined as the lowest layer of the overcast or broken. So there's different types of clouds. It's usually sky clear. We then have a few clouds, scattered clouds, broken, and then also overcast, which would be like a solid layer. So you guys we'll cover the clouds as we move forward to weather, but just know that anytime that you have a ceiling less than 1,000 feet or the visibility is less than 3 statute miles, then you have to be operating pretty much in the IFR world. If you don't have an instrument rating, it's pretty much going to be off limits. The IFR world is basically going to allow you to fly through the clouds, in the clouds, and you don't have any really visibility or ceiling requirements. The main things is that you fly solely by reference to looking at your instruments versus VFR. We fly solely by basically looking out the window 90% of the time and then backing that information up by looking at our instruments. So IFR is kind of the next step after your private pilot license. We call that the instrument rating, where it allows you to fly in or under the instrument flight rules. And it basically takes you or allows you to get in and out of airports in the conditions that you see on the left, where the one on the left, that is probably going to be IFR taking a look at it. So even moderate rain can reduce the visibility below 3 statute miles. Okay. The whole premise and the reason why we have all these different requirements above a cloud, below a cloud, and everything else is the whole premise of the system is known as see and avoid. Your number one responsibility as a pilot is to see and avoid other aircraft. Okay. And by being certain distances and having certain visibility or being able to see far enough, then you should be able to see VFR traffic and IFR traffic coming out of the clouds or anything else. Okay. So that is kind of the basics of your VFR and IFR. All right, what I want everyone to do is take a quick sec, and I want you to draw this triangle. So grab a blank piece of paper. We're going to reference this triangle as we go through the PowerPoint today. This is going to help you memorize the weather requirements. So I'll give everyone a couple seconds on that. You do not have one already. So a couple of questions. Al, if you get trapped above, nope, cannot. You're stuck. Obviously, if you declare an emergency and go into the clouds. So the reason why they don't, you have very limited training flying via instruments. You're required to have 3 hours, but, a non-instrument rated pilot, I think the average time is as soon as you enter a cloud, it's 90 seconds before you spin, kind of do that graveyard spin. So just because you don't have the training. All right, everyone have their piece of paper out? For those that are challenged with drawing these things, very simply, just start with a triangle. Make sure that it's large enough or taking up the majority of the paper so you have enough room. And then after you draw that other triangle, draw an inverted triangle within that one, just like that. And then you can draw that line to the left here, to the right here, okay? All right, so what we're gonna do with this is basically the base of the triangle is representing the ground, and the very, very tippy top or the apex of the triangle is the equivalent of 18,000 feet. So these are basically different altitudes that we wanna know. The top of the inverted triangle right here is going to be 10,000 feet MSL. And then the line, the horizontal line on the lower right triangle is basically representing 1,200 feet AGL or above ground level, okay? So what we're gonna do is we're gonna fill out this triangle as we basically cover each type of airspace here. So the main thing that we can kind of do ahead of time is I'm gonna draw a nice poofy cloud in the top one here. And then I'm gonna draw a nice poofy cloud that kind of dissects those two lines here, okay? You should have something that looks like this. The triangle exercise grant is at the very back of Airspace, so you can actually reference that at the very end. All right, everyone got that? I don't have the grant. I don't know the page. Just go to Airspace section in Rod Machado's book. It is the last page of Airspace. It's the very, very last page of Airspace. All right, now that we've got something that looks like this, put this aside, and we're going to reference this over the next 30 minutes here. And this is kind of the old way of teaching the FAA. This is how everybody learned, like, 20, 30 years ago. Okay, we would all stare at this chart and try to memorize everything with all these different types of airspace, and then kind of look at the system. And it's, I don't know, some people like this. Actually, very, very few people like this, and it's kind of convoluted. But the basic premise is that we have all these different types of airspace: Alpha, Bravo, Charlie, Delta, Echo, and then Golf. Don't ask me what happened to Foxtrot; it's not included. But at the end of the day, there's actually only two different types of airspace. There's controlled airspace, which is all the letters A through E at the top, and uncontrolled airspace, which is G. The primary difference is that in controlled airspace, you can basically get air traffic control services. So different types of things, flight following. You can also get local air advisories. We'll talk about what that means later. In uncontrolled airspace, you're not going to get those services. It doesn't mean that air traffic control cannot see you on their radar, but they're not going to be able to provide any type of traffic separation or sequencing services or anything along those lines. So that's the primary differentiation, okay? Controlled airspace, the first one we'll talk about is altitude, and that's going to be our class Alpha airspace. That's really all the airspace between 18,000 feet and above. Then we've got our class Bravo airports, which are our big, busy airports. You can kind of use these as mnemonics: big, busy, Boeing, anything like that. They look like an upside down cake, and you can see that they have multiple layers. They're not always going to be shaped this way. It depends on the geography and where they're actually located. So they might be kind of odd looking at the end of the day. Pretty much any major airport you can think of: Atlanta, Chicago, Dallas, Miami, all the New York airports, LA, San Francisco, all of them. Those would all be class Bravo airports. And we'll show you actually how to identify that. The next one down from a Bravo is going to be your class Charlie airports. And we usually say these are crowded. They're not as big or busy as the class Bravos. They usually have 2 layers to them, and they're typically going up to 4,000 feet. AGLs are about 4,000 feet tall. They also have a control tower. That is what is representing in these 3 here. And then D is for dialogue. So you can kind of think of it as D and higher, basically class Delta and higher airspace. You will have to talk with someone to get into that airspace. Okay, you're gonna have to talk with some air traffic controller to do, or basically get within there. Class Echo is all of the space in between all the other airspaces that you guys see here, all of the blue in between this. The big thing to kind of keep in mind is that as we kind of go up from class Echo to class Alpha, what ends up happening is that the airspace becomes more congested. There's more airplanes. There are greater requirements. There's more chit chat and talking and dialogue that needs to happen. And then you're going to get more and more air traffic control services as you basically go back up to your class Alpha. Okay. Then finally is class Golf, which is your go for it. You know, you can basically go for it. It's kind of like the Wild West. Class Golf will for the most part, pretty much only goes up to 1,200 feet high, or what we call 1,200 feet AGL. There's one circumstance where it will go higher. We'll talk about that moving forward. Okay. So what we're going to do is we're going to kind of pick these off one by one here and talk about them. We'll take care of class Alpha, which is the easiest one to kind of talk about. So class Alpha starts at 18,000 feet MSL, and it's going to go all the way up to 60,000 feet MSL. These are all going to be considered in the flight levels. So you could basically say, what we abbreviate is flight level 180 to flight level 600 is 18 to 60,000 feet. This is going to extend 12 nautical miles off the coastline within the lower 48. And the main thing with class Alpha is that you guys unfortunately cannot fly there. Okay. In order to fly within class Alpha airspace, you will need the following. You're going to need to obviously have an instrument rating. That's number one. And number two, you've got to be on an IFR flight plan. Only aircraft above 18,000 feet are in an instrument flight plan, and those pilots have to have an instrument rating. So probably not a problem for most of us. Most of our GA airplanes, you can maybe get to 12 or 14,000 feet. But if you got all the bells and whistles and bought, you know, one of these super planes out there and you got the money, unfortunately, until you get your instrument rating, you're going to be limited below 18,000 feet. Okay. That's the easy one to kind of knock off. And if you remember the pyramid, there's really nothing to draw on the pyramid, but basically everything up here is the class Alpha. There is actually no weather requirements up there because everybody is IFR. So we don't care about clearances or distance away from clouds or visibilities or anything else as we go through it. Okay. So let's go ahead and continue here and see if you guys can answer this question. I'm hoping for 100%. In which type of airspace are VFR flights prohibited? Got the first third in. About 70%. All right. Apologize if I cut off anybody. We got 97% with the correct answer. A couple people got it incorrect, but that's fine. Correct answer is class Alpha airspace. Keep in mind when I'm giving you guys test questions, this should be obvious at this point, but I'm not going to try to give you a test question with anything we haven't covered. And we definitely have not covered Bravo or Charlie yet. So, but great job for everybody that got it correct there. All right, so let's now talk about the next one. The next type of airspace, and we're not going to necessarily go in alphabetical order here, is going to be airspace that's called Class Echo airspace. So the red is going to be your alpha. Okay, so we can't get up there, and it starts at 18,000 feet. So the two ways to kind of think of Class Echo is you can think of it as like hanging off of Class Alpha, basically hangs down from Class Alpha. And it has the ability to extend all the way down to 3 different levels, of course. It's never that easy, okay? Majority of Class Alpha is going to go all the way down to 1,200 feet AGL. And remember, AGL is above ground level. It also has the ability to go to 700 feet AGL. And then it also has the ability to go all the way down to the ground. Okay, so it looks something like this. Pretty much the majority of Class Echo will be going down to 1,200 feet AGL. So the way that we typically talk about Class Echo for the most part is going to be that Class Echo starts at 1,200 feet AGL, and it extends up to, and there's two ways to say this. You could say up to, but not including 18,000 feet, or you can say it extends up to 17,999. Okay. The reason why is you cannot have overlapping or competing airspace because Class Alpha starts at 18. So the other one, like I said, is you could have it extend down to 700 feet AGL, or it could extend all the way down to the surface. And we're going to look at each one. The way that we're able to tell this is we're going to be able to look on the map. And on the map, we're going to find different types of either magenta. It's either going to be a magenta solid line, a dashed line, or a shade. And then the same thing with the blue, the cyan solid, dashed, or a cyan blue is going to have a different indication of the different types of airspaces. Okay. So before we do that, we want to talk about Class Echo airspace because it has the ability to go above 10,000 feet and also below 10,000 feet. And we're going to skip that for a second because I'm going to take you to back to the triangle. Very simply, in the middle of your triangle, you should have something that says 10,000 feet MSL. It's that line that basically separates the top portion from the bottom portion. In the top portion, anytime you're above 10,000 feet, we want to remember this mnemonic. You are more likely to see above 10,000 feet an F-111, which looks something like that. Okay. Anytime that you're below 10,000 feet, you're more likely to see 3 Cessna 152s. Okay, 3 Cessna 152s because they barely can get up to 10,000 feet, on a good day. Okay, so what we're going to do is we're going to use these mnemonics to our benefit here, and we're going to go back to, before we continue how to identify the information, we're going to go back to our chart. And remember, like I said, the two that we care about is the F-111 and the 3 Cessna 152s below 10,000 feet. So the F-111 is going to basically transfer to this. It's going to mean 5 statute miles of visibility. Okay. We've got 1,000 feet above a cloud, 1,000 feet below a cloud, and 1 statute mile horizontally from the cloud, left or right. Okay. And Class Echo can exist all the way up to, but it doesn't include 18,000. So it goes in that top box, which is from 10,000 up to, but not including 18. And then in the upside down triangle, I am going to put Class Echo here as well. Leave yourself enough room. We might move some of these letters around. And when I'm below 10,000 feet, I am more likely to see 3 152s. So that means it's 3 statute miles of visibility. Okay. 1,000 feet above a cloud, 500 feet below a cloud, and 2,000 feet horizontally from a cloud. Okay. I promise you this works because if you print these out, the blank ones, and try to fill this out, and if you do it 10 times, I guarantee you'll memorize all the weather requirements rather than trying to do it with some of these other crazy charts that are out there. Okay. And this is 100% will be on your check ride. And also will be on your exam as well. All right, so now that we have that, it's basically the same thing here. So, depending on how visually you are, basically what I showed you guys back there, same thing, 1,000 feet above, 1,000 feet below, 1 mile horizontally. Okay. The reason why you have greater requirements above 10,000 feet is the speed. There is no speed limit. The only speed limit above 10,000 feet is you can't unfortunately, you can't go beyond the speed of sound. Okay. So anything below 10,000 feet, you're limited to 250 knots. We'll talk more about that on Monday when we get into regulations. So because aircraft are converging much, much faster above 10,000 feet, they're telling you need more time to see them, which means you need greater visibility requirements, 5 statute miles instead of 3 statute miles. And we want you further away from a cloud should an aircraft pop out of a cloud. That way you have at least a second or two to modify your course. All right, so the first one we're going to talk about is Class Echo that starts at 700 feet. Um, Anytime that you see these, they kind of look like keyholes. In this example here, we can identify if it's going to start at 700 feet due to the magenta shade. And really what it's doing is it's protecting the aircraft as a transition area, if you want to call it that. It's really used for instrument approaches and those types of things. So it keeps them within the controlled airspace as they descend. So very simply, as they're basically making their way to the airport, they can stay within controlled airspace. Because remember, if the airplane goes outside of controlled airspace, then they can't, they lose their ATC services or air traffic control services. So basically works on the arrivals and departures for whatever that environment is. So what that actually looks like on your 2D map would be something like this. So very simply, if we're standing at Creston Airport, kind of looks like a keyhole. If we were to pull up the approach going into Creston, there's actually an instrument approach that goes pretty much a straight in like that. And as the airplane basically descends, it's giving it a lower altitude than the surrounding airspace. That way it can keep it within that controlled environment. Now this airport does not have an operating control tower. We can tell that because of the magenta color. If it was that bluish cyan color, then it would. And very simply, when we're talking about the shading, it's always going to be the hard side of the shading in. So when we look at it, basically everything within this little keyhole here would be considered Class E, which would basically, we would say it starts at the 700-foot AGL, and then it goes up to, but does not include 18,000 feet. Okay, goes up to, but does not include 18,000 feet. The next one that you might have is you might actually have a few different ones that are kind of overlapping. Okay, so majority of Class Echo airspace will start at 1,200 feet. We know that the magenta shade is going to allow it to go down to 700 feet. And if you've got a magenta dashed line, it'll actually start at the surface. And what this is doing is, once again, it's allowing you that aircraft, it's not really for you guys, but it's allowing an aircraft to transition on their instrument approach, basically going lower and lower to the ground and being able to stay within controlled airspace as it does so. Okay. So what that looks like would be this. And what you're going to notice here is that we have a magenta shade on the exterior here. I've kind of highlighted it out. And then the main one I want to point out is the dashed line. So anything within this dashed magenta dashed line means that Class Echo is going to start at the surface and go up to, but not include 18,000 feet. Okay, up to, but not include 18,000 feet. So very simply, if I am standing at the airport right here, I'm looking and I want to know what airspace I'm in, going to be Class Echo from surface up to, but not including 18,000. If I am standing right here, you'll notice that I'm outside of the dash line, but I'm inside of the shade. That means that the Class Echo is going to start at 700 feet AGL and go up to, but not including 18,000 feet. If I was standing right here at this abandoned airport, that's the circle with the X there, then that means that Class Echo starts at 1,200 feet AGL and goes up to, but does not include 18,000 feet. It's only going to go lower than 1,200 feet AGL if you see the shade or you see the dashed line. Those are the only two times it goes lower than 1,200 feet. Okay. All right, so that is Class Echo in a nutshell. Okay, the next one that we're going to talk about is the wonderful world of Class Golf. So beneath Class Echo is going to be your Class Golf airspace. This is your uncontrolled airspace. Class Golf will usually start at the surface and go up to 1,200 feet where Class Echo starts. Okay, if Class Echo starts at 700 feet, AGL, then right beneath that is going to be Class Golf. If Class Echo starts at the surface, you can't have another airspace starting below the surface. So that kind of takes that out of the equation. So Class Golf is uncontrolled. There's a lot less restrictions there. And in terms of the cloud clearance requirements, they are definitely a little bit more convoluted when we look at it. Okay. So we'll kind of go through the Class Golf environment here and kind of show you what that looks like. Class Golf, there's only one time that it's actually charted, and it's kind of the specialty here. This is all of your basically your cloud clearance requirements. I think it's a little convoluted as well. So I'm going to take you back to our triangle and we'll see if we can figure out another way. Okay. So for Class Golf has the ability it always starts at the surface, and it has the ability occasionally, I say occasionally, like very occasionally, go up to 14,500 feet. And I'll show you that in a second. So what we have to do is we're going to start off on the lower right-hand side of the triangle. And what we're going to do is I'm going to put a G, horrible G, looks like a 6. Put a G over here. It's even worse. And this is going to represent Class Golf on the lower right triangle. Okay. So Class Golf generally starts at the surface and goes up to 1,200 feet AGL. And if you're flying in Class Golf from the surface up to 1,200 feet AGL, then very simply what you need to do is you need to have 1 statute mile of visibility. I'm just going to put a slash here and remain, I'm going to put this COC is going to be my abbreviation for clear of clouds, CLOUDS. Okay. So 1 statute mile clear of clouds. And clear of clouds means that you can get as close as you want to a cloud as long as no part of the aircraft actually goes in it. So if you want to be like 2 inches away from a cloud and you can maintain that distance, then that's perfectly acceptable. Okay. The 1 statute mile of visibility and clear of clouds. That's the requirement. Anytime you're above 1,200 feet AGL, but you're below 10,000 feet, because that marker is the very tip here, inside of Class Golf, you need to have 1 statute mile of visibility. And guess what? The cloud clearance distances are the same, 1,000 above, 500 below, and 2,000 feet horizontally. And if you happen to be in that Class Golf that rarely occurs above 10,000 feet, we're going to put another letter up here. It's Echo and Golf. It's the same requirements as Echo. So it's 5 statute miles, 1,000 above, 1,000 below, and 1 statute mile horizontally. Finally, on the lower left-hand pyramid or triangle here, this is also Class Golf, but this is Class Golf at night. Okay, it has a separate, they've got a daytime requirement and they've got nighttime requirements. The only one that has day and night. So very simply, you're going to draw a moon. Hopefully that looks like a moon. I always have to write the word moon because some people don't know my drawing. And effectively, any time that it's at nighttime from the surface to 10,000 feet, you can draw an arrow to the center upside down triangle. It's going to revert to the center triangle, which is 3 statute miles of visibility, 1,000 above, 500 below, and 2,000 feet horizontally. Okay, so there's a number of different requirements for Class Golf. Okay. Everybody good so far? My moon banana. Yep. I'm not an artist. Sorry, guys. The other way of thinking about it, I had a student a number of years ago with my in-person ground school. They loved Coke and all things Coke, like not obviously Coca-Cola. What they used to say was that you're more likely when you're in Class Golf in this area below 1,200 feet, you're more likely to knock over 1 Coke machine is the way that he remembered it. Because you're flying so close to the ground and because it's pretty much nothing out there. There's only going to be 1 of them. So you can come up with whatever mnemonics that you want or whatever memory aids that you want. Okay. Mike, I understand it's confusing. I'll tell you how to break it down here in just a few minutes. Let me finish golf and then we'll wrap this up. And then when we come back on Monday, we'll pick it up and do the controlled airspaces. I'm sorry, Bravo, Charlie, and Delta. All right. So let's talk about that crazy Class Golf that has the ability to go up to 14,500 feet. Okay. So this is pulled from an old chart. If you looked on an old Los Angeles sectional chart, I don't know, I think they stopped this in 2018-ish. You wouldn't find this anymore. Okay. So this is Bishop Airport. This is, I don't know, 100 miles south of South Lake Tahoe area, right next to Mammoth. And what we've got is this blue fade or this tint here. So this right here, that little blue shade, everything to the left of that hard line is effectively telling us that Class Golf starts at the surface and it goes up to 14,500 feet. okay, up to 14,500 feet. So if I were standing at Bishop Airport, let's go through a quick review here. Bishop Airport is an uncontrolled airport. It does not have a control tower. It has a magenta shade surrounding it, so I know that Class Echo starts at 700 feet. So if I were standing right there, what I could tell you is that from surface to 700 feet AGL is Class Golf, and then Class Echo starts at 700 feet AGL, goes up to, but does not include 18,000 feet. And that's basically true pretty much within this entire corridor that you guys see right there. If I'm standing right by Freeway or Highway 6 right there, there is no shading anywhere around that. Then what that's telling me is that if I'm standing at my car there, from the surface up to 1,200 feet AGL is Class Golf, and then everything above that is Class Echo. If I'm standing right here, to the left of that hard shaded line, then it's Class Golf from surface to 14.5, and then everything above 14.5 up to but not including 18,000 is Class Echo airspace. Okay, gonna take some practice. One thing I do want to point out, though, is I understand this is one that always throws people because we talked about Class Golf traditionally going from the surface up to 1,200 feet AGL or 1,200 feet AGL, right? One thing that I like to show students is we're just going to look on SkyVector here real quick and pull this up. If we were to look at an IFR chart, and you guys will not have to know anything about IFR charts until you actually get your instrument rating. But the reason why I want to pull it up is that Class Golf on IFR charts is actually shown in a gray shading if it goes from the surface up to 14.5. So right here, where my mouse is kind of circling towards the bottom middle of the screen right there, there's one little place, I believe that's out by Arizona. There's also some along the border and also a little bit further up north. So here's our friends to the north. We can see some spots up there, and there are some kind of hidden in between. If we looked at this map, and I had a couple students that gave me some really old, like 1980s maps of Oregon. Pretty much the entire state of Oregon was Class Golf from surface up to 14,500. But the one thing I'll kind of point out for you is that we don't necessarily have to worry about it as much anymore because they are disappearing. Radar is more prevalent, and in addition to that, it's harder for us to hide. So this was really, when we had radar issues and things where they couldn't necessarily provide air traffic control services. Anyways, if I scroll down and look at this, and I actually go back to our VFR map, you're going to see that there is a blue shade where this box is currently located. And this is what we would see on your VFR chart. So basically what it's telling us is the entire portion of space, basically within this, whatever that trapezoid or whatever that figure happens to be, is going to be from surface up to 14,500 is going to be Class Golf. Okay. If I were standing by this airport, which is outside of that blue box, the hard line, and this is the Springfield Municipal Airport, basically from surface to 700 feet would be Class Golf, and then it would turn into Class Echo, and we know that because we have this magenta shade that surrounds it. Okay. If I looked at this private airport here, the White Mountain Private Airport, there is no shading. There's nothing really there. It's just by itself. This would be Class Golf from the surface to 1,200 feet because there's no shading in and around it. And then it would become Class Echo from 1,200 up to, but not including 18,000, or sometimes you could just say up to 17,999. So that is kind of it in a nutshell. If we kind of go back to the PowerPoint here that I was showing you a second ago, I cleared the lines. If we were to look at this same image on the map for Bishop in California, they've actually removed all of the Class Golf up to 14.5. So this was actually removed in 2017. Most of the mountain range was 14.5. And the reason why the U.S. chose 14.5 was Mount Whitney was one of the highest mountains in the U.S. So it was either just shy of 14.5 or just close to it. So at the end of the day here, I also want to show you guys this because we're not going to have time to wrap up all of the airspace today. And I understand this stuff can be challenging. And what I would not recommend is don't try to memorize everything in one go. The first thing that I tell students to do is see what you can identify on the actual sectional chart. So take a look at, if you have a physical sectional chart, take a look at that. If you don't, then just go to Sky Vector and see what you can identify beyond just the airspace. What is the little yellow by what is a Shao Low is, or Pinedale, or Clay Springs? What does the line here mean? Is that a road? Is that electrical lines here? Make sure that you can identify everything on the chart. After that, start looking at the airports, right? So we talked about the airports with these little tick marks here. So Taylor Airport, we can have a tick to the east, the west, and the south. That basically represents that there's fuel or services on that airport, versus White Mountain Lake, which is just a circle. There are no services at that particular airport. Once you kind of have the basics down, the next thing that I would recommend, go back to the PowerPoint. I stole this from our other presentation the other day as well, is that at the end of the day, even though we have not covered some of the other airspace, there's really only 2 colors of airspace and really just 3 different potentials, okay? So they're either going to be a dashed line, a solid line, or a shaded line, right? So that's really it. And you either have magenta or it's going to be cyan. So the bluish color is cyan, the magenta color is that nice purple color that they have over there. And some of the dead giveaways that you're always going to be able to find is going to be with Class Delta, which we have not yet covered today. It's always going to be a blue dash line, and there's going to be some numbers in basically a box, or what looks like a box, and that's going to tell you how high the Class Delta goes. So no other airspace has that. Class Bravo airspace always has a solid blue line. These are for our larger airports, and somewhere along the edge you will see the name of the Class Bravo. That's the same thing with Class Charlie. That's a solid magenta line. On the flip side of that, if we look at the magenta colors, if it's a dashed magenta line, then Class Echo starts from the surface and it goes up to, but does not include 18,000 feet. If it is the shaded portion, what we just looked at Taylor Airport, then Class Echo starts at 700 feet AGL and then goes up to, but does not include 18,000. So everything below 1,700 is going to be Class Golf. So just like what we looked at a second ago here, when we look at Taylor Airport one more time, let me bring that one on the screen. You'll see that Taylor has that magenta shade that we just looked at. So very simply, here is Taylor Airport. We can see the circular magenta shade on the exterior of it. So basically everything within this area is going to be Class Golf from surface to about 700, and then from 700 up to, but not including 18,000, is going to be Class Echo. So what I would encourage you to do is don't try to bite off the entire, don't take it, take small bites. Let's just say it that way. Understand what is on the map, make sure you can identify it, and then once you can kind of figure out, okay, that's a Class Echo, that's a Class Bravo, etc., then come back to our airspace triangle and then start talking about the weather requirements. So we have blank copies of the airspace triangle within the lesson, so just scroll down beneath the live stream and you'll see a couple blank versions of these. Most students are able to, if you can fill these out about 10 times from memory, you'll basically have everything memorized that you need to know in terms of the requirements, all right? There's still some additional requirements that we're going to talk about, and that's going to kind of lead into federal aviation regulations when we come back on Sunday. So keep that in mind. This is technically our Friday, if you will, but we'll restart everything in 2 days on Sunday at the same time. Right, so hopefully that'll give you some guidance of what to practice over the weekend. When we come back on Sunday, we'll basically pick up the remainder of the airspace and what's known as special use airspace, try to put it all together, and then we'll move on to the regulations moving forward. With that, as always, I hope everyone enjoyed the first week of class. You're about 25% of the way done. As always as well, if you want to take a college attempt at basically, trying the old, lesson 3 airspace here, you're more than welcome to do so. If you want to hold off until we cover the remainder of the material on Sunday, you're more than welcome to as well. All right, I'll stick around for any questions, but other than that, everybody is free to go. Hope everyone has a fantastic weekend moving forward. Let's see, when talking about or below cloud clearances, we're saying either, so it's all inclusive. So when we say 1,000 feet above, 1,000 feet below, and 1 statute mile horizontally, that's in reference to the actual aircraft as well, right? Drew, you're very welcome. Sergio as well. Andrew, Gary, absolutely. So this is just practice, practice, practice. People get frustrated with this, but unfortunately, you just have to sit there with the map and try to identify things on there. try to use those strategies that I gave you. There's only there's only 2 colors and 3 different combinations, right? So you either have solid magenta, solid, dashed, or a faded line. So just kind of work within those. Yep, your brain hurts, everybody. I totally get that. Eric, Ken, Melanie, you're very welcome. Jay Garrett as well. Nathan, Eric, Mike, your brain is a little jelly. I think that's the reason why I used to always throw that little lemur in there that you guys probably saw from the previous class. So I understand completely how that feels at the end of the day. Okay. You're very welcome, Chip. If you have any questions that we weren't able to get to in the meantime, keep in mind that you have Ask a CFI if it's aviation related as well. Use the tips and tricks, the F-111, like Hang said, and the Cessna 152, the 3 152s below 10,000 feet. I will try to put a few other aviation airspace videos in our newsfeed as well. So take a look at those. I try to put videos that were related to what we're covering during the class period. A lot of people, sometimes they need additional materials, which is fine. Yep, you remember the lemur, Lucas, exactly. So just like that. Slowly starting to make sense. I'm glad to hear it, Patrick, David, you're welcome as well. Awesome, Mike, appreciate it. Good night, Lucas. All right, so with that, I am going to go ahead and sign off for the night. As I said before, I hope everyone stays safe, enjoy their weekend, couple days off here. We'll see you back on, going to be on Sunday, trying to get my days of the week here correct. And we'll be back at 2 p.m. Pacific Coast time, which is going to be 5 p.m. East Coast time. Okay. Donald, you're working all your monitors there. Awesome. And the FAA test links do not open. Is there a trick to open it? The test link, I'm assuming, Tanya, you're talking about the FAA testing guide. That should link up. Travis can double check it for you. If not, if you go into the Ask a CFI, I think it's the 3rd discussion point. I've got a forum in there that says FAA testing supplements in the event you had trouble accessing it as well. Right? Thanks again to all the mods and everybody else. Have a great weekend out there, and we'll see you later. We'll leave the chat open for a few more minutes, let you conclude any last-minute conversations, and have a great weekend once again.